You cannot outrun the universe, not with the fastest rocket ever built, not with a spacecraft moving at 430,000 miles per hour, not even if you pushed that machine to 99.999% of light speed, burning fuel that does not yet exist, riding physics most engineers still call science fiction. Because while you are racing toward the stars are racing away from you. And they are winning. Right now, the fastest human-made object in history is screaming through space at a velocity that sounds impossible. It would cross the United States coast to coast in less than 10 seconds. And at that speed, reaching the nearest star system would still take 6,000 years. That is not a technology problem. That is a universe problem. The distances between stars are so obscenely large that even our most extreme achievements in speed are effectively standing still. For decades, that fact has sat like a wall at the edge of every conversation about interstellar travel. A boundary that seemed absolute, unbreakable, final, but Einstein left a door open. Buried inside the equations of special relativity is a loophole so strange, so fundamentally disorienting that it changes the entire game. It does not let you move faster. It does something far more unsettling. It changes what time means. And if you are willing to pay the price, if you are willing to step through that door and accept what it costs, you can cross the Milky Way in a single human lifetime. You can watch 100,000 light years collapse into decades. You can become a traveler who sees the galaxy up close while everyone and everything you ever knew turns to dust behind you. And even that is not enough, because the universe has one more rule, one final limit, and it is closing in. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. We have built the fastest machine humanity has ever launched into space. We pointed it at the sun, let gravity yank it downward, and watched it scream past our star at speeds no human-made object has ever achieved. The Parker Solar Probe, at its peak velocity, reaches roughly 430,000 miles per hour. That is fast. That is faster than anything we have ever done. It is a triumph of engineering, a monument to human ambition, and by the standards of our species, it is blindingly, impossibly quick. By the standards of the universe, it is standing still. If you fired that probe at Alpha Centauri, the nearest star system to our sun, it would arrive in about 6,000 years. 6,000, that is longer than all of recorded human history. That is longer than the entire span from the first Sumerian clay tablets to the device you are holding in your hand right now. Launch it today, and it would reach its destination sometime around the year 8000. No one alive would see it arrive. No one alive would remember the people who built it. The civilization that launched it would be dust, its languages forgotten, its cities erased, its entire cultural lineage reshuffled a dozen times over. And that is just to reach the nearest star. The Milky Way galaxy is about 200,000 light-years across. A light-year is the distance light travels in 1 year, moving at roughly 670 million miles per hour. Nothing in the universe moves faster. Light does not accelerate. It does not build up speed. It simply moves at that rate, always, everywhere, with no exceptions. And even at that speed, crossing our galaxy from edge to edge would take 200,000 years. Not 200,000 years at Parker Solar Probe speed, 200,000 years at light speed, the fastest thing physics allows. That is the gap we are trying to cross. That is the ocean we are trying to sail with a rowboat and a dream. Let us start with what fast actually means. Voyager 1, launched in 1977, is currently about 15 billion miles from Earth, moving at roughly 38,000 miles per hour relative to the Sun. It is the most distant human-made object in existence. It has been traveling for nearly 50 years. It has left the solar system. It is out there in interstellar space, coasting through the void between stars, farther from home than anything we have ever built. And at its current speed, it would take Voyager 1 roughly 73,000 years to reach Alpha Centauri, assuming, of course, that it were actually headed in that direction, which it is not. It is aimed at a completely different patch of sky, drifting toward a star called AC plus 793888, which it will pass in about 40,000 years at a distance of about 1.6 light-years, close in cosmic terms, meaningless in human ones. The Parker Solar Probe is faster, significantly faster. But even at 430,000 miles per hour, the numbers do not get better in any way that changes the fundamental problem. 6,000 years to the nearest star, 60 million years to cross the galaxy at that speed. 60 million. Our species has only existed for about 300,000 years in its modern form. Civilization as we recognize it has been around for maybe 10,000. The entire history of complex multicellular life on Earth spans roughly 600 million years. You would need to run that entire evolutionary timeline again, from the first worms in the mud to the first spacecraft leaving the atmosphere, just to cross the galaxy once at the fastest speed we have ever achieved. Alpha Centauri is not some distant exotic location at the far edge of the universe. It is our neighbor. It is the star system next door. From our perspective, it is practically sitting on our front lawn, and we cannot reach it in any time frame that would matter to a human being. Imagine standing on a beach and looking out at an island on the horizon. You can see it clearly. You know it is there. You have telescopes that can resolve details on its surface, count its trees, map its coastline. Now imagine that the fastest boat you can build would take 6,000 years to reach it. That is where we are. That is the scale of the problem. The solar system, by comparison, is tiny. It sounds enormous when you list the numbers. The Sun to Neptune is about 2.8 billion miles. Pluto at its farthest gets out to about 4.6 billion miles. The heliopause, the boundary where the solar wind gives way to interstellar space, sits at roughly 11 billion miles. Voyager 1 crossed it in 2012. These numbers feel big because they are big by human standards. But interstellar space does not start at the heliopause. Interstellar space starts when you leave the Sun's gravitational neighborhood entirely, and that neighborhood extends much, much farther. The Oort cloud, a vast spherical shell of icy debris surrounding the solar system, stretches out to somewhere between 1 and 2 light-years from the Sun. 1 light-year is about 6 trillion miles, so even leaving the solar system in the true gravitational sense means crossing at least 6 trillion miles of empty space before you are genuinely in the space between stars. At Voyager 1's speed, that takes 30,000 years. At Parker Solar Probe's speed, maybe 3,000. Still longer than human civilization. Here is another way to think about it. If you shrunk the solar system down to the size of a US quarter, a coin about an inch across, the nearest star would be sitting about 300 feet away. That is a football field. Walk from one end zone to the other, and you have just crossed the interstellar gulf from our Sun to Alpha Centauri. Now shrink yourself down to the scale of the Parker Solar Probe on that same map. You are not even a speck. You are smaller than a bacterium, and you are trying to walk the length of a football field. At your top speed, it would take you 6,000 years. That is the geometry of interstellar space. That is what fast means when the distances involved are measured in light years. People talk about space being empty, but that is not quite right. Space is not empty. It is just incredibly, stupendously, unreasonably big. There is matter out there. Hydrogen atoms, a few per cubic centimeter on average in interstellar space, dust grains, the occasional molecule, magnetic fields threading through the void, cosmic rays zipping along at relativistic speeds. But the distances between objects that matter, stars, planets, anything you could actually visit, are so vast that the matter in between becomes irrelevant. You are not traveling through a medium, you are traveling through geometry. And the geometry does not care how clever your engine is. The fastest natural objects we know of are particles accelerated by supernova shockwaves and black hole jets. Some of them move at 99.99% of light speed or higher. Even those particles, if they were aimed at Alpha Centauri, would take just over 4 years to arrive. 4 years is better than 6,000. It is incomparably better. But it is still 4 years at a speed nothing made of matter and held together by chemical bonds could ever survive. A spacecraft moving that fast through even the thin interstellar medium would be sandblasted into plasma within seconds. Every hydrogen atom it hit would strike with the energy of a particle beam weapon. The cosmic rays alone would shred anything biological on board down to the molecular level. So even if you could build an engine capable of accelerating a ship to near light speed, and we have no idea how to do that, you would still need to solve the problem of not being destroyed by the universe you are trying to move through. This is the part where someone usually brings up nuclear propulsion, antimatter engines, solar sails, ion drives, all the technologies that show up in documentaries and science fiction as the bridge between here and the stars. And yes, those technologies are real, or at least theoretically real, and yes, some of them could in principle get us moving faster than chemical rockets ever will. A nuclear pulse drive, the kind that detonates atomic bombs behind a spacecraft to push it forward, could maybe reach a few % of light speed. That would cut the travel time to Alpha Centauri down to a century or so. Still longer than a human lifetime, but within the range of a multi-generational mission. A spacecraft pushed by a massive laser array, a concept called breakthrough starshot, could in theory accelerate a tiny probe to 20% of light speed and reach Alpha Centauri in about 20 years. That sounds almost reasonable. Except the probe would weigh about a gram, carry almost no instruments, have no way to slow down when it arrived, and would zip past its target so fast it would have maybe a few hours to take pictures before disappearing into the darkness beyond. And the laser array required to push it would need to be about the size of a small country and consume more power than most nations generate in a year. It is not a plan. It is a thought experiment with a budget in the trillions and an engineering checklist that starts with rewrite physics and ends with good luck. The problem is not that we lack ambition. The problem is not even that we lack technology, though we certainly do. The problem is that the universe is constructed at a scale that makes ambition irrelevant. You can be as ambitious as you want. You can have all the technology in the world. You can solve every engineering challenge between here and Alpha Centauri, and you will still be trying to cross a football field one bacterium-sized step at a time. The scale wins. It always wins. Light itself takes 4.24 years to reach Alpha Centauri. That is the floor. That is the absolute minimum time anything, a signal, a ship, a message in a bottle, could take to get there. And light does not need fuel. It does not need to accelerate. It does not need to carry supplies, repair itself, navigate, or avoid obstacles. It just goes. We are not light. We are fragile sacks of chemistry that need food, water, air, and protection from radiation. We need living space. We need reasons to stay sane. We need a way to survive not just the journey but the decades or centuries of isolation that come with it. Even if we could build a ship that traveled at 90% of light speed, and we cannot, the people on board would still spend years in transit, with no way to turn around, no way to call for help, and no guarantee that anything resembling a habitable destination would be waiting when they arrived. And that is just to the nearest star. The galaxy is 200,000 light-years across. There are roughly 400 billion stars in the Milky Way, scattered across a disk so wide that even light, moving at its absolute maximum speed, takes 200 millennia to traverse it. If you wanted to visit the far side of the galaxy, you would need to travel for longer than modern humans have existed as a species, longer than Neanderthals walked the Earth, longer than Homo erectus learned to use fire. You would leave during one era of Earth's history and arrive in another, assuming Earth was still there, assuming the sun had not changed, assuming anything you left behind still remembered you existed. Most likely, none of that would be true, so why bother? Why even think about this? If the distances are insurmountable, if the technology does not exist, if the timescales involved are longer than empires, why are we talking about traveling to the stars at all? Because the numbers change, not the distances, those stay fixed. But the experience of traveling those distances changes depending on how fast you are moving. And this is where things stop being depressing and start being strange. Because Einstein figured out more than a century ago that time itself is not a constant. It bends, it stretches, it slows down for objects moving at high speed relative to objects standing still. And if you can get a spacecraft moving fast enough, close enough to light speed, something extraordinary happens. The universe outside keeps aging at its normal rate, but inside the ship, time dilates, it runs slower. The journey that takes thousands of years for the rest of the galaxy takes decades or years, or in extreme cases even less for the people on board. You do not break the light speed limit, you do not cheat causality, you just take advantage of the fact that time is relative. And if you can push a ship close enough to light speed, you can cross the galaxy in a human lifetime. Not the galaxy's lifetime, yours. That is not science fiction. That is physics. Proven, tested, measured physics. We have watched particles moving at near light speed in accelerators live longer than they should because time slows down for them. We have flown atomic clocks on aeroplanes and watched them tick slightly slower than clocks left on the ground. The effect is real, and at the speeds we are talking about, the effect is not small. It is enormous. At 99.999% of light speed, time dilation becomes so extreme that you could cross the Milky Way in 50 years of your own time. 50 years, a human lifetime. While 200,000 years pass outside, the stars you left behind will have died. The civilizations you knew will be gone. But you, inside that ship, will have aged only 5 decades. You will have crossed a galaxy, and when you arrive, no one will be waiting. That is the prison we live in. That is the map of our reality. 60 million years to cross the galaxy at the fastest speed we have ever achieved, 6,000 years to reach the nearest neighboring star, and 200,000 years for light itself to traverse the Milky Way from edge to edge. Those are the numbers, those are the walls, and for most of human history, that would have been the end of the conversation. The universe is too big, we are too slow. Close the book, go home. Accept that the stars are pretty, but fundamentally unreachable in any time frame that would matter to a species with a lifespan measured in decades. That was the state of things until 1905. Then a 26-year-old patent clerk in Bern, Switzerland, who had been spending his spare time thinking about light, published a paper that broke the universe open. His name was Albert Einstein. The paper was called On the Electrodynamics of Moving Bodies. It was 17 pages long, contained no references, and introduced a theory so strange and so counterintuitive that even some of the best physicists of the era initially dismissed it as nonsense. Today we call it special relativity, and it tells us something extraordinary. The distances do not change. The galaxy is still 200,000 light-years across. Alpha Centauri is still 4.24 light-years away, but the time it takes to cross those distances, at least from the perspective of the person doing the traveling, is not fixed. It bends, it compresses, it shrinks down to almost nothing if you can move fast enough. You do not cheat the universe. You do not break the speed limit. You just take advantage of the fact that time itself is not the rigid universal constant everyone assumed it was. Time is negotiable, and the negotiation starts with light. Before Einstein, physicists assumed light worked like sound. Sound is a wave that travels through air. No air, no sound. Light, they figured, must be a wave traveling through some invisible substance that fills all of space. They called it the luminiferous ether. The idea made sense. Waves need a medium. Water waves move through water. Sound waves move through air. Light waves, logically, should move through ether. The problem was that nobody could detect the ether. No experiment could measure it. No instrument could find it. And worse, if the ether existed, then the speed of light should change depending on how fast you were moving through it. If you were traveling in the same direction the light was moving, you should measure it going slower. If you were traveling toward it, you should measure it going faster. That is how speeds add up in everyday life. If you are on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the ground sees the ball moving at 70 miles per hour. Speeds add. That is obvious. That is intuitive. That is how the universe should work. Except when two physicists named Albert Michelson and Edward Morley actually tried to measure the speed of light while the Earth was moving through the ether. They got the same number no matter which direction they pointed their apparatus. The speed of light did not change. It was the same in every direction, at every time, regardless of how fast the Earth was moving. That result made no sense. It violated every intuition about how motion should behave, and it sat there for nearly 2 decades like a thorn in the side of physics, unresolved and inexplicable. Einstein looked at that result and made a choice that would reshape everything. He said, "Fine. The speed of light is constant, not approximately constant. Not constant under certain conditions, constant, always, for every observer, no matter how fast they are moving. If you are standing still and you measure the speed of light, you get 299,792,458 meters per second. If you are on a spaceship moving at 90% of light speed, and you measure the speed of a light beam moving in the same direction, you do not get 10% of light speed. You get the full speed of light, the exact same number. That is the first postulate of special relativity. The speed of light in vacuum is the same for all observers in inertial reference frames. That sentence does not sound revolutionary until you think about what it implies. If the speed of light is always the same, and you cannot make it go faster or slower by changing your own speed, then something else has to give, and the thing that gives is time. Here is the simplest way to see it. Imagine a clock made of light. Take 2 mirrors, place them parallel to each other, 1 meter apart. Fire a photon from the bottom mirror straight up toward the top mirror. The photon bounces back down, bounces back up. Tick, tock, that is your clock. 1 tick is the time it takes light to travel 2 meters, about 6.6 nanoseconds. Now put that clock on a spaceship. The spaceship is moving to the right at a significant fraction of light speed. You are standing outside the spaceship, watching it go by. From your perspective, the photon is no longer moving straight up and down, it is moving diagonally. The ship is moving forward while the photon travels from the bottom mirror to the top mirror. So from your perspective, the photon has to cover a longer path. The light travels up, but also sideways, because the mirrors themselves are moving sideways as the photon bounces between them. The total distance the photon travels, from your perspective, is longer than 2 meters, but the speed of light is constant. It has to be, that is the rule. The photon cannot move faster to compensate for the longer path, so the only way the math works is if the clock ticks slower. From your perspective, standing outside the moving ship, 1 tick of the light clock takes longer than 6.6 nanoseconds. The clock on the ship is running slow, not because something is wrong with it, not because it is broken, but because time itself is passing more slowly on that ship than it is for you standing still. That is time dilation. The faster the ship moves, the longer the diagonal path becomes, and the slower the clock ticks. At low speeds, the effect is tiny, negligible. A car moving at 60 miles per hour experiences time dilation of about 1 part in a trillion, undetectable without atomic clocks. But as the speed increases, the effect grows, and as the speed approaches the speed of light, the effect explodes. Physicists measure this with a number called the Lorentz factor, usually written as the Greek letter gamma. The formula is 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At low speeds, gamma is very close to 1. That means time is passing at nearly the same rate for you as it is for someone standing still. The faster you go, the larger gamma gets, and as your speed gets closer and closer to the speed of light, gamma shoots upward without limit. At 90% of light speed, gamma is about 2.3. That means for every hour that passes on your ship, 2.3 hours pass outside. At 99% of light speed, gamma is about 7. 1 year for you is 7 years outside. At 99.9% of light speed, gamma is about 22. At 99.99%, gamma is about 70. And at 99.9999% of light speed, the number we will come back to later, gamma is about 707. 1 year of your time equals 707 years outside. 1 decade equals 7,000 years. 50 years of subjective time equals 35,000 years in the rest of the universe. The curve is exponential. It does not climb steadily. It sits low for a long time and then it launches into the stratosphere as you get within a fraction of a percent of light speed. That is the loophole. That is the trick Einstein handed us. You cannot go faster than light. Nothing with mass can. The energy required to accelerate an object grows without limit as you approach light speed, which means hitting light speed exactly would require infinite energy. It is not a technological limit. It is not an engineering problem. It is a hard wall written into the structure of space-time itself. But you do not need to go faster than light. You just need to go fast enough that time slows down dramatically for you while the rest of the universe ages normally. From the outside, you are still taking thousands or even hundreds of thousands of years to cross the galaxy. But from your perspective, inside the ship, you are aging at a fraction of that rate. The galaxy does not get smaller. You do not cheat the distances, you cheat time. Einstein did not invent this to help us reach the stars. He was not thinking about interstellar travel. He was trying to resolve a contradiction in Maxwell's equations and the null result of the Michelson-Morley experiment. The fact that his solution also provides a theoretical path to crossing galactic distances in a human lifetime is an accident. A beautiful, tantalizing, physically valid accident. And it is not just theory. We have tested this repeatedly. In 1971, physicists Joseph Hafele and Richard Keating took 4 cesium atomic clocks, the most precise timekeeping devices available at the time, and flew them around the world on commercial airliners, 2 flights, one eastward, one westward. When they brought the clocks back and compared them to reference clocks that had stayed on the ground, the flying clocks had ticked at slightly different rates. The eastward clocks, which had been moving faster relative to the center of the Earth because they were traveling in the direction of Earth's rotation, had lost time. The westward clocks, which had been moving slower relative to the Earth's center, had gained time. The differences were tiny, a few hundred nanoseconds, but they matched the predictions of special relativity exactly. Time dilation is real. It happens to anything that moves. You just do not notice it at human speeds because the effect is so small. You notice it in particle accelerators. Physicists smash protons into each other at speeds higher than 99.999% of light speed. At those speeds, gamma is enormous. Particles that normally decay in microseconds live for milliseconds or longer because time is passing more slowly for them. The particles do not know they are living longer. From their perspective, they are decaying on schedule. But from our perspective, watching from the lab, their clocks are running in slow motion. We see them travel farther, survive longer, live extended lives purely because they are moving fast. The effect is not subtle. It is the difference between a particle that should decay after traveling a few meters and a particle that travels kilometers before decaying. The only thing that changed was the speed. Time did the rest. You notice it in orbit. The Global Positioning System, GPS, relies on a constellation of satellites circling Earth at an altitude of about 20,000 km. Each satellite carries an atomic clock. The clocks need to stay synchronized to within a few nanoseconds, or the position data they send to your phone will be off by meters or more. But the satellites are moving at about 14,000 km per hour relative to the surface of the Earth. At that speed, special relativity predicts their clocks should run slower than clocks on the ground by about 7 microseconds per day. At the same time, general relativity, Einstein's later theory, predicts that because the satellites are farther from Earth's gravity well, their clocks should run faster than ground clocks by about 45 microseconds per day. The two effects do not cancel. The general relativistic effect is larger. So the net result is that satellite clocks run about 38 microseconds per day faster than ground clocks. 38 microseconds does not sound like much, but light travels about 300 meters in 1 microsecond. If you did not correct for relativity, GPS would accumulate errors of about 10 km per day. Your navigation app would be useless. Every satellite in the GPS constellation is programmed to tick at a slightly slower rate than it naturally would, so that by the time the signal reaches Earth, the clock appears synchronized with ground time. Relativity is not a theoretical curiosity. It is baked into the infrastructure of modern life. Your phone corrects for time dilation every time you check a map. So what happens when you push this to the extreme? What happens when you stop talking about satellites moving at a few kilometers per second and start talking about starships moving at 99.999% of light speed? The math is straightforward. Plug the numbers into the Lorentz factor and the universe bends. At 99.999% of light speed, gamma equals 707. Travel for 1 year at that speed, and 707 years pass in the rest of the galaxy. Travel for 10 years and 7,000 years pass outside. Travel for 50 years and 35,000 years pass. But here is the thing, 50 years is a human lifetime. Not a long one, not a short one. Just a lifetime, a career. A span of time you could actually experience, start to finish, and remain the same person at the end of it. You would not need to freeze yourself. You would not need to put your consciousness into a computer. You would not need generation ships where your descendants carry on the mission after you die. You could board the ship as a young adult, live through the journey, and step off on the far side of the galaxy as a middle-aged person. And when you looked back at Earth, it would be gone, not destroyed, just irrelevant. The sun you left behind would have aged 35,000 years. The continents would have shifted. The ice caps would have melted and refrozen a dozen times. Civilizations would have risen and collapsed. Languages would have evolved into unrecognizable forms. Entire species would have gone extinct. New ones would have emerged, and nobody, not a single living thing on that planet, would remember the day you left. Einstein's equations do not care about your feelings. They do not care that this creates a one-way trip. They do not care that you would be stepping into a future where nothing you knew still exists. They just tell you what the clocks will read, yours and theirs. Relativity does not give you a way to go faster than light. It gives you a way to skip forward in time. You become a ghost. You slip through the centuries like a stone skipping across water. The universe outside keeps running at normal speed. You, inside the ship, experience less of it. That is the trade. That is the price. And it is not negotiable. Time dilation is not a technology you can turn on and off. It is not an engine you fire up when you want to go fast. It is a consequence of velocity. Move fast enough and time slows down. There is no opt-out. There is no reversal. When you step onto a relativistic starship, you are stepping into the future. And the only way back is to turn around, accelerate again to near light speed, and skip forward even further. Every trip you take adds centuries to the calendar. Every journey is a leap into the unknown. NASA tested this from another angle. In 2009, the Fermi Gamma Ray Space Telescope detected 2 photons from a gamma ray burst 7 billion light-years away. The photons arrived 900 milliseconds apart. Gamma ray bursts are among the most energetic events in the universe. They release more energy in a few seconds than the sun will emit in its entire lifetime. The photons Fermi detected had different energies. If space-time were not smooth, if it were grainy or foamy at the smallest scales the way some quantum gravity theories predict, then higher energy photons might interact with that graininess and travel at slightly different speeds than lower energy photons. The difference would be tiny, but over 7 billion light-years it would add up. The photons would arrive at noticeably different times. They did not. They arrived within a fraction of a second of each other after traveling for 7 billion years. That is not just a confirmation of relativity. That is a confirmation that space-time itself is smoothed down to scales smaller than anything we can currently probe. Einstein's prediction held. Light speed is constant. Space is not lumpy. The photons that left that gamma ray burst 7 billion years ago, when the universe was half its current age, traveled at exactly the same speed the entire way. No detours, no slowdowns, no exceptions. Another test came from measuring electrons. A team of physicists pushed an electron to extreme speeds in a particle accelerator and measured whether its maximum velocity changed depending on which direction it was moving. If there was some preferred direction in space, some hidden structure or asymmetry, the electron might move slightly faster or slower depending on its orientation. They measured the electron's speed in multiple directions to within 17 nanometers per second. That is about 10 times more precise than previous measurements. The speed was the same in every direction, no variation, no hidden asymmetry. The universe does not care which way you point. Light speed is the same everywhere, in every direction, for every particle. That is the foundation, that is the bedrock, and it is that bedrock that allows time dilation to work. The strangest part is that none of this feels strange when you are the one moving. If you are inside a spaceship traveling at 99.999% of light speed, your clocks tick normally, your watch works fine, your heart beats at its usual rate, you age 1 second per second, you do not feel slow, you do not feel compressed. You do not look out the window and see the universe frozen in time. From your perspective, you are sitting still and the rest of the universe is moving past you at 99.999% of light speed. And because of that, the rest of the universe is time dilated, not you, them. That is the symmetry of relativity. There is no absolute rest frame. There is no privileged observer. Every observer sees themselves as stationary and everyone else as moving. You think their clocks are slow, they think your clocks are slow. Both of you are right. The paradox only resolves when one of you accelerates, because acceleration breaks the symmetry. Acceleration is absolute. You can feel it. It shows up in every reference frame. And when you decelerate at the end of your journey and come to rest relative to the galaxy again, that is when the asymmetry becomes clear. You aged 50 years, the galaxy aged 35,000. The math does not lie, the clocks do not lie. The universe outside moved on without you. That is the loophole. That is the gift Einstein left us. It is not a way to go faster. It is a way to experience less time while covering the same distance. The photons that left a star 200,000 light-years away took 200,000 years to get here from the perspective of someone standing still. But if you were riding alongside one of those photons, if you could somehow experience the journey from the photon's perspective, the trip would take 0 time. Photons do not experience time. They are born, and they arrive in the same instant from their own frame of reference. You cannot be a photon, you have mass, but you can get close. Close enough that the 200,000 light-years between one side of the galaxy and the other compresses down into something a human being could survive. 50 years, maybe less. Not because the galaxy got smaller, because your clock slowed down. The destination is still 200,000 light-years away for everyone else. For you, it is 5 decades of subjective experience. That is not cheating. That is physics. Cold, hard, tested, confirmed, undeniable physics. The universe allows it. The question is whether we can build a machine capable of reaching those speeds and what we are willing to give up to use it. So what does that actually look like? What happens when you stop treating relativity as a curiosity on a chalkboard and start treating it as a set of engineering constraints for a starship that needs to cross the galaxy in something resembling a human lifetime? The math we already covered tells you the time dilation part. At 99.999% of light speed, gamma equals 707. 1 year on the ship equals 707 years outside. 50 years inside equals 35,000 outside. That is the headline number. That is the number that shows up in the documentaries and the thought experiments. But it is also misleading because that number assumes you are already moving at 99.999% of light speed. It does not tell you how you got there. It does not tell you how long the acceleration took. And it definitely does not tell you what happens when you need to slow down at the other end. Because here is the thing nobody mentions when they talk about crossing the galaxy in 50 years. You do not just point your ship at the far side of the Milky Way, hit the gas and coast. If you did that, you would arrive at your destination moving at 99.999% of light speed with no way to stop. You would zip past whatever you were trying to reach so fast that you would have maybe a few seconds to take pictures before vanishing into the intergalactic void beyond. A relativistic flyby is not a mission. It is a very expensive way to take blurry photographs. So any realistic mission profile has to include acceleration and deceleration, and that changes everything. Let us start with the simplest version. You want to cross the Milky Way. The galaxy is about 100,000 light-years across. You are starting from Earth, somewhere out in the suburbs about 25,000 light-years from the galactic center. You want to reach the far edge, another 75,000 light-years beyond the center. Total distance, 100,000 light-years. You want to do this in a single human lifetime. Let us say 50 years of ship time, and you want the people on board to experience something close to normal gravity during the trip so they do not spend decades floating in zero-G watching their bones dissolve. The standard thought experiment uses 1G acceleration. 1G is the acceleration you feel standing on Earth right now, 9.8 meters per second squared, comfortable, familiar. Your body knows how to handle it. The plan is this. You accelerate at 1G for the first half of the trip. Halfway across the galaxy, you flip the ship around and decelerate at 1G for the second half. By the time you arrive, you have burned off all your speed and you are moving slowly enough to actually stop and look around. This is called a brachistochrone trajectory, which is a fancy Greek way of saying the shortest time path. It is not the shortest distance, it is the path that gets you there in the least amount of subjective time for the people on board. And the math on this has been worked out in detail because physicists love nothing more than solving impractical problems to 15 decimal places. At 1E acceleration, it takes about 1 year of ship time to reach 90% of light speed. You are still accelerating, still building velocity, still feeling that comfortable push into your seat. After 1 year, you are moving fast enough that time dilation starts to become noticeable. After 2 years, you are at about 98% of light speed. After 3 years, you are pushing 99%. The curve gets steeper. You are adding smaller and smaller increments of velocity, but those increments cost more and more energy because you are climbing up against the relativistic mass increase. Your ship is not getting heavier in the sense that it has more atoms. But it is getting harder to accelerate because energy and mass are equivalent, and the kinetic energy you are pumping into the ship shows up as effective mass from the perspective of anyone trying to push you faster. By the time you hit year 10 of continuous acceleration, you are moving at better than 99.99% of light speed. And here is where it gets interesting. You are still accelerating. You are still feeling 1G. From your perspective inside the ship, nothing has changed. You have been sitting in your chair feeling normal Earth gravity for a decade. But outside, the galaxy is no longer the shape you remember. Length contraction has kicked in. The Lorentz transformation does not just stretch time, it compresses space. Distances in the direction you are traveling shrink by the same factor that time dilates. If gamma is 700, then a distance of 100,000 light-years in the rest frame of the galaxy looks like 100,000 divided by 700 in your frame, about 140 light-years. You have not moved faster than light. The galaxy has not physically shrunk. But from your perspective, the distance you need to cover is shorter. You are moving at 99.9999% of light speed relative to the galaxy, and the galaxy is compressed along your direction of motion into something that looks more like a flat disk than a sprawling volume. Stars that were separated by thousands of light-years now appear bunched together. The entire 100,000 light-year span from one edge to the other has collapsed into a corridor you could cross in months if you did not need to slow down. That is the trick. That is how the journey becomes survivable. You do not experience the full 100,000 light years. You experience a compressed version of it. The trip that takes 100,000 years from the perspective of someone sitting still in the galaxy takes about 50 years from your perspective, because you are experiencing both time dilation and length contraction. Time is running slower for you. Space is shorter for you. Both effects work in your favor. The galaxy still measures 100,000 light years across if you stop and measure it with a ruler after you arrive. But during the trip, while you are moving, it is shorter. You are not breaking physics. You are just traveling through a version of space-time that has been warped by your velocity. This is not an illusion. It is not a trick of perception. The contraction is real. It is measurable. If you could somehow freeze the universe mid-journey and take a snapshot from your reference frame, the galaxy would be flattened. If you pointed a telescope backward at Earth, assuming you could still see it, the light from Earth would be blue shifted into a tight cone directly behind you. If you pointed a telescope forward, the stars ahead of you would be red shifted and smeared into a glowing ring around the direction of travel. The sky would not look like a sky. It would look like a tunnel. A bright halo in front of you, where all the stars in your forward direction have been Doppler shifted and compressed into a single glowing band. Darkness to the sides because the light from stars at right angles to your motion is being left behind, and another dimmer halo behind you where the stars you passed are stretched and fading. The faster you go, the tighter the forward ring becomes. At extreme speeds, your entire view of the universe collapses into a shrinking circle of light directly ahead, while everything else fades into infrared and radio. So you accelerate for 25 years at 1G, halfway across the galaxy. Then you flip the ship. You rotate 180 degrees, so your engines are now pointed in the direction you are traveling, and you fire them again. Now you are decelerating. The force you feel is still 1G, still pushing you into your seat, because deceleration and acceleration feel the same when the engines are doing the work. You spend the next 25 years slowing down. By the time you reach the far side of the galaxy, you have burned off all that speed. You are moving at a few kilometers per second relative to the local stars, slow enough to stop, slow enough to actually explore whatever you came here to see. Total subjective trip time, 50 years. You boarded the ship as a 20-year-old. You step off as a 70-year-old. You lived a normal human life. You experienced every day of those 50 years. You did not sleep through them. You did not freeze yourself. You aged. You thought. You ate meals. You had conversations. You read books. You got bored. You looked out the window. You did all the things a human does during 50 years of existence. The only difference is that outside the ship, 100,000 years passed. Maybe more, depending on the exact mission profile and how close to light speed you actually got during the peak velocity phase. That is the trade. That is the cost of the journey. You arrive at your destination, and the civilization that built your ship is gone. The people who waved goodbye are dead. Their children are dead. Their children's children are dead for 1,000 generations. The languages they spoke have evolved into something unrecognizable. The nations they lived in have collapsed and been replaced and collapsed again. The continents have shifted. The climate has changed. The night sky from Earth looks different because stars have moved. Some of the stars visible from Earth when you left are no longer visible. Some that were not visible are now up there, bright and obvious. Entire stellar cycles have played out. Stars have been born. Stars have died. Supernovae have exploded. Nebulae have formed and dispersed. And the Sun, the star you grew up under, has aged 100,000 years. It is still there. It is still burning. But it is 100,000 years older. It is slightly brighter, slightly hotter. The habitable zone around it has shifted outward. If Earth is still inhabited, the people living there are not your descendants. They are not your species. They might not even be biological. 100,000 years is longer than anatomically modern humans have existed. It is longer than Neanderthals existed. It is longer than Homo erectus existed. It is 4 times longer than the entire span of recorded history. You have not traveled to another place. You have traveled to another era, and there is no going back. That is what people mean when they talk about the twin paradox. It is not really a paradox, it is a prediction. You have a twin, you get on a spaceship, your twin stays on Earth. You accelerate to near light speed, travel across the galaxy, turn around and come home. When you step off the ship, you have aged 50 years. Your twin, if they were somehow still alive, would have aged 100,000 years, except they are not alive. Nobody is. Your twin died 99,950 years ago. That is not a paradox. That is just what the math says happens. The confusion comes from the symmetry. Special relativity tells you that all inertial motion is relative. If you are moving at constant velocity relative to me, I can say you are moving and I am standing still. Or I can say I am moving and you are standing still. Both descriptions are equally valid. So if I am on the ship and you are on Earth, I can say your clock is running slow because you are moving relative to me, and you can say my clock is running slow because I am moving relative to you. We are both right. So when we meet up again, whose clock actually shows less time? The answer is that the symmetry breaks as soon as someone accelerates. Acceleration is not relative. Acceleration is absolute. You can feel it. It shows up as a force. If you are sitting in a windowless room and you feel yourself being pushed into your chair, you know you are accelerating. You do not need to look outside. You do not need a reference point. The acceleration is real and measurable in your own frame. The traveling twin is the one who accelerates. They fire their engines. They turn around. They decelerate. The stay-at-home twin does not. The stay-at-home twin just sits there in an inertial frame the whole time, coasting through space on a planet that is not accelerating in any significant way. So when the twins reunite, it is the traveling twin who has experienced less time. The math is unambiguous. The traveling twin aged less. The stay-at-home twin aged more. And the difference is not small. At relativistic speeds, the difference is measured in millennia or more. This is not speculation. This is tested physics. We have flown atomic clocks on aeroplanes and confirmed that they tick slower when they move. We have sent particles around accelerators at near light speed and watched them live longer than they should because time is passing slowly for them. We have satellites in orbit that correct for time dilation every day. The twin paradox is not a paradox. It is a prediction that has been confirmed over and over in every test we have ever run. The only reason it sounds weird is because we do not live at relativistic speeds. We live in a world where the fastest thing we ever experience is a jet aeroplane moving at a few hundred miles per hour. At those speeds, time dilation is real but unmeasurably small. You do not notice it. Your body does not feel it. Your clocks are not precise enough to detect it without atomic-level accuracy. But scale up the speed, and the effect scales with it. At 99.999% of light speed, the effect is not small. It is the dominant fact of your existence. So what does a mission profile actually look like? You need a ship. The ship needs engines. The engines need fuel. And here is where the numbers stop being inspiring and start being impossible. To accelerate a ship to near light speed, you need energy, a lot of it. The kinetic energy of an object is 1/2 mass times velocity squared in the classical approximation. But at relativistic speeds, the formula changes. The energy grows without bound as you approach light speed. One estimate from a physics forum calculated that to accelerate a ship to 99% of light speed using a perfect photon drive, meaning you are converting matter directly into light and shooting it out the back for thrust, you would need a fuel-to-ship mass ratio of about 10.5 billion to 1. That is not a typo. 10.5 billion kilograms of fuel for every kilogram of ship. If your ship weighs 1,000 kilograms, about the mass of a small car, you need 10.5 trillion kilograms of fuel. That is roughly the mass of a small asteroid. And that is just to reach 99% of light speed. To reach 99.9999%, the ratio gets worse, much worse, exponentially worse. You are trying to climb an energy curve that goes vertical. Every additional 9 you add to your velocity costs you orders of magnitude more fuel. At some point, the fuel you need weighs more than the observable universe. That is the wall. That is the reason we do not have relativistic starships sitting in orbit waiting for passengers. The workaround people talk about is not carrying your fuel. If you do not have to carry it, you do not have to accelerate it, and your mass ratio drops dramatically. One idea is a laser-pushed sail. You build a giant sail, probably made of some kind of reflective metamaterial that can survive being blasted by terawatts of laser light without vaporizing. You attach your ship to the sail. Back home, you build an array of lasers in space, maybe powered by solar panels the size of a small country. You point the lasers at the sail and you turn them on. The light hits the sail, transfers momentum, and pushes the ship forward. Keep the lasers running for years or decades, and you can accelerate the ship to a significant fraction of light speed without carrying any fuel on board. The problem is, you cannot slow down. Once the ship is out of range of the lasers, it is coasting. If you want to stop at the destination, you need a second laser array already waiting at the other end to decelerate you, which means someone has to build that array, which means someone has to get there first, which means this only works if you have already colonized your destination, which defeats the purpose of sending the ship in the first place. Some proposals suggest using a magnetic sail that interacts with the interstellar medium to brake. The idea is that you deploy a huge loop of superconducting wire, run a current through it to generate a magnetic field, and let that field drag against the charged particles drifting through space. It is a brake made of magnetism. The problem is the interstellar medium is thin, a few atoms per cubic centimeter. The drag force is tiny. Slowing down from near light speed using a magnetic sail would take centuries or longer, and your ship has to survive that whole time without hitting anything solid, because at relativistic speeds, even a dust grain hits like a bomb. That is the other problem nobody talks about. Space is not empty. It is mostly empty, but mostly is not the same as completely. There are hydrogen atoms out there. There are dust grains. There are small rocks. There is debris left over from dead stars and exploded planets. Most of it is tiny. Most of it is harmless if you are moving at normal speeds. But if you are moving at 99.999% of light speed, every hydrogen atom you hit strikes your hull with the kinetic energy of a particle beam. A single grain of dust, something the size of a speck of sand, hits with the energy of a nuclear weapon. Your ship does not just need engines and fuel and life support. It needs armor. It needs shielding. It needs some way to sweep the space in front of it clear of debris or deflect incoming particles before they punch through the hull and vaporize everyone on board. One proposed solution is a magnetic field projected ahead of the ship that deflects charged particles. Another is a cloud of plasma pushed out in front like a bow wave, absorbing impacts before they reach the hull. Another is just a massive block of solid matter, maybe ice or rock, held out in front of the ship as a sacrificial shield. All of these add mass, all of them add complexity, and none of them have been tested because we have never built anything that moves fast enough for this to matter. Then there is heat. At relativistic speeds, even the cosmic microwave background, the faint glow of radiation left over from the Big Bang, blue shifts into visible light and then into X-rays. The universe around you is no longer a cold 3-degree Kelvin void. It is a furnace. The faster you go, the hotter it gets. You are flying through a radiation field that from your perspective is thousands or millions of degrees. Your ship needs cooling, a lot of it. You need radiators the size of football fields just to dump the waste heat from the particle impacts and the blue shifted background radiation, and those radiators are targets. Every square meter of surface area you expose to space is another place where a dust grain can punch through. The engineering problems stack on top of each other until the whole concept starts to look less like a starship and more like a city-sized engineering project that needs to function perfectly for decades with no resupply, no repairs, and no margin for error. One mistake and everyone dies. One system failure and the mission is over. One micrometeorite in the wrong place and the ship disintegrates at a significant fraction of light speed, scattering debris across a light year of space in a thin, expanding cloud that no one will ever find. And yet the physics allows it. That is the frustrating part. The universe does not forbid this. Relativity does not say you cannot do it. It just says that if you do, you will experience time dilation and length contraction and all the other weird consequences of moving at extreme speed. The laws of physics are fine with you crossing the galaxy in 50 years. They just do not care whether you can build a machine capable of doing it. The math works, the engineering does not. Not yet, maybe not ever, but the possibility is there, written into the structure of space-time. Waiting for someone clever enough, or desperate enough, or crazy enough to figure out how to turn equations into hardware. And if they do, if someone somewhere actually manages to build a ship that can accelerate to 99.999% of light speed and survive the journey, they will step off that ship into a galaxy that has aged 100,000 years without them. They will be explorers in the truest sense, not just explorers of space, but explorers of time, leaping forward through the centuries, skipping across the timeline like a stone across water, watching the universe evolve in fast forward while they sit in their tiny metal bubble, experiencing every second at normal speed. They will see things no one else will ever see. They will go places no one else will ever reach. And when they arrive, no one will be waiting. No one will remember their names. They will be ghosts, echoes, refugees from a distant past, stepping into a future they cannot predict and cannot return from. That is what relativity offers, not faster than light travel, not a shortcut, just a way to trade your present for someone else's future, a one-way ticket to the other end of time. So you built the ship. You solved the impossible engineering problems. You gathered the fuel, or you figured out how to not need fuel. You assembled a crew crazy enough to volunteer. You strapped yourself into a chair inside a metal tube full of spinning gyroscopes and fusion reactors and enough concentrated energy to vaporize a small moon. You fired the engines. You felt that one gee push into your back as the ship began to accelerate, smooth and steady like an elevator heading up, and you left. You looked back through a porthole, if your ship even has portholes, and you watched the Earth shrink from a world to a marble to a dot to nothing. You watched the sun become just another star. You watched the solar system, the only home your species has ever known, compress into a point of light, and then fade into the background glow of the Milky Way. And you kept going. For 25 years, you accelerated. For 25 years after that, you decelerated. You crossed the galaxy. You arrived at your destination, some distant star system on the far side of the spiral arm, and you did whatever it was you came to do. Maybe you found something. Maybe you built something. Maybe you just looked around, took notes, planted a flag. And then, because you are human and humans are sentimental creatures who cannot help themselves, you decided to go home. You turned your ship around. You pointed it back toward Earth. You fired the engines again. Another 25 years of acceleration, another 25 years of deceleration, 50 years out, 50 years back, 100 years total of your subjective time. You aged 1 century. You boarded the ship young. You are stepping off old, but alive, coherent, still yourself, still carrying memories of the place you left behind. And when you step off that ship and look up at the sky above Earth, if Earth is even still called Earth, 100,000 years will have passed. That is the trade, that is the cost of the round trip, and no one prepared you for what that actually means. The math is clean. Time dilation does not care about your feelings. You travel at 99.999% of light speed for 50 years and the universe outside ages 35,000 years. Do it twice, once out and once back, and you have skipped forward 70,000 years. Add in the time spent at your destination, the time spent accelerating and decelerating at slightly lower speeds during the early and late phases of the journey, and you are easily past 100,000 years of external time. The clocks do not lie, the equations do not lie. But equations do not tell you what it feels like to be the only person left alive from your century. They do not tell you what it feels like to come home and find that home is gone, not destroyed, not abandoned, just moved on, replaced, forgotten, paved over by 10,000 generations of people who have no idea you ever existed. You are not a returning hero. You are an artifact, a fossil that still breathes, a ghost that walked out of a museum. Here is what you will not find when you get back. You will not find your family. Everyone you knew is dead. Your parents dead, your siblings dead, your children, if you had them, dead. Your friends, your neighbors, your co-workers, the person you bought coffee from every morning, the stranger you smiled at on the train, every single human being who was alive the day you left, dead. Not recently dead, long dead, ancient dead. Dead for so many generations that even the memory of them has been forgotten. Genealogies do not go back 100,000 years. Written records do not go back 100,000 years. Oral histories do not go back 100,000 years. The entire span of recorded human history, from the first Sumerian tablets to the present day, fits inside 6,000 years. 100,000 years is 17 times that length. You have skipped forward past the entire ledger of everything humanity ever wrote down, and then you kept going. You are not returning to a different decade. You are not even returning to a different millennium. You are returning to a different epoch. If your descendants are still around, and that is a big if, they are not your descendants in any sense you would recognize. The genetic line has been reshuffled so many times that every living human on Earth is equally related to you. You are the ancestor of everyone, or the ancestor of no one. Either way, nobody knows your name. You will not find your language. Languages change, fast. English as it was spoken in the year 1000, Old English, is completely unintelligible to a modern English speaker. Beowulf was written in Old English. Try reading it in the original sometime. It looks like a different language because it is a different language. Middle English, the language of Chaucer, written around 1400, is barely comprehensible. Shakespeare, writing around 1600, is difficult but readable. That is 600 years of linguistic drift. Now multiply that by 160. 100,000 years is 160 times longer than the gap between Old English and Modern English. Whatever people are speaking when you get back, it is not English. It is not descended from English in any traceable way. It is not even descended from the same language family. The Indo-European languages, the family that includes English, Spanish, Hindi, Russian, Persian, all evolved from a common ancestor spoken maybe 6,000 years ago. 100,000 years is long enough for languages to evolve, split, diverge, go extinct and be replaced a dozen times over. When you step off your ship, you will not understand a single word anyone says. You will not be able to read the signs. You will not be able to ask for help. You are functionally illiterate in your own homeworld. You will not find your nation. Countries do not last 100,000 years. Empires do not last 100,000 years. The longest continuously existing institution in human history is arguably the Catholic Church, which has been around for about 2,000 years. That is 2% of the time you were gone. The Roman Empire lasted maybe 1,500 years, depending on how you count it. 1.5%. The United States has existed for less than 300 years. 0.3%. The oldest known city, Jericho, has been continuously inhabited for about 11,000 years. 11%. That is the upper bound. And those are individual cities, not nations. Political borders shift constantly. Governments rise and collapse. Ideologies come into fashion and fade into irrelevance. When you get back, the political map of Earth will have been redrawn so many times that the very concept of nations might not even exist anymore. Maybe humanity unified into a single global entity. Maybe it splintered into 10,000 independent city-states. Maybe it abandoned the surface entirely and moved into orbital habitats. Maybe it left Earth altogether and the planet is a nature preserve. You do not know. You cannot know. Because the thing you left behind, the geopolitical structure of the early 21st century, lasted maybe another few hundred years after you left, and then dissolved into something else. You will not find your city. Cities burn, cities flood. Cities get buried under sediment and volcanic ash and the slow, patient grinding of tectonic plates. Earthquakes topple buildings, rivers change course, coastlines shift as ice caps melt and refreeze, sea levels rise and fall. Over 100,000 years, the physical geography of Earth changes. Not dramatically, not in ways that would make the continents unrecognizable, but enough. Enough that the street you lived on is gone, the building you worked in is gone, the park you walked through is gone. Maybe someone built a new city on the same spot and it has the same name. Maybe they did not. Maybe the site of your hometown is now underwater. Maybe it is under a glacier. Maybe it is a desert. 100,000 years ago, the Sahara Desert was green. It was covered in lakes and grasslands. The climate shifted. The monsoon rains moved south. The whole region dried out and became the largest hot desert on the planet. That kind of change happens on timescales much shorter than 100,000 years. When you come home, you will not recognize the landscape. You will look for landmarks and find nothing. The hills will be in the wrong places. The rivers will have moved. The forests will have grown and been cut down and grown again 1,000 times. You are standing on Earth, but it is not the Earth you remember. You will not find your culture. Music, art, literature, fashion, religion, philosophy, the entire superstructure of meaning that made your society what it was, gone. Not suppressed, not banned, just obsolete. replaced by newer ideas, and then replaced again and again and again. The plays of Sophocles are 2,500 years old, and we still read them, but only because a tiny fraction of ancient Greek literature survived through deliberate preservation efforts by people who thought it was important. Most of it is lost. 99% of everything ever written in ancient Greek is gone. Burned in fires, lost in wars, crumbled into dust, simply not copied often enough to survive. And that is only 2,500 years. 100,000 years is 40 times longer. Nothing survives that's spanned by accident. If any fragment of your culture is still around when you get back, it is because someone, many, many generations after you left, decided it was worth preserving. And they probably misunderstood it. They probably interpreted it through the lens of their own time and their own values, and turned it into something you would not recognize. You are not returning to your culture. You are returning to a world where your culture is at best a footnote in a historical database that nobody reads. You will not find your stuff. Your house is gone. Your possessions are gone. Every object you owned, every photo you took, every letter you wrote, every piece of clothing you left in a closet, gone, decayed, rusted, rotted, recycled, thrown away by strangers who moved into your house after you left and had no idea who you were. Your bank account is closed. Your money is worthless. The currency you earned does not exist anymore. The financial system that backed it collapsed thousands of years ago. Your property deeds mean nothing. Your legal identity is not in any database. You do not have a social security number that anyone recognizes. You do not have a birth certificate that any institution will accept. As far as the legal and financial infrastructure of Earth is concerned, you do not exist. You are not a citizen. You are not a resident. You are not a documented person. You have no proof of who you are because the systems that would have verified your identity are gone. You will need to convince someone, somehow, that you are a time-displaced space traveler from 100,000 years in the past, and you will need to do that without speaking the language. So what do you have? You have your memories. You have the interior experience of 100 years of subjective time. You remember what Earth looked like when you left. You remember the faces of people who are now dust. You remember buildings that have been gone for millennia. You remember songs no one has heard in 10,000 generations. And you have your ship, assuming it still works, assuming you can land it, assuming there is anyone down there who knows what a ship is or why you came back. You are the loneliest human being who has ever lived. Not because you are physically alone. There might be billions of people on Earth when you get back. Maybe trillions if they figured out how to expand into space. You are lonely because you are separated from every other living person by a gulf of time so vast that no common reference point exists. You cannot talk about your childhood because your childhood happened in a world that no longer exists. You cannot talk about your job because the economy that job was part of does not exist. You cannot talk about your favorite movie because the entire medium of film may have been replaced by something else centuries ago. Every conversation you try to have will dead end in confusion and translation errors and the slow dawning realization that you have nothing in common with these people. They are human, you are human, but you are from different worlds. This is not a new problem. Humans have always understood that time separates us. Rip Van Winkle fell asleep for 20 years and woke up in a world that had moved on without him. That is a fairy tale, but it captures something real, the fear of being left behind, the fear of waking up and discovering that the world you knew is gone. But Rip Van Winkle slept for 20 years. You were gone for 100,000. The scale is so different that the analogy breaks down. 20 years you can recover from. People remember you. Records still exist. The language is the same. The country is probably still there. you can reintegrate, you can catch up. 100,000 years, there is no catching up. There is no reintegration. You are not rejoining society. You are joining a completely new society that has no memory of the one you left. You are an immigrant from the past, and here is the worst part. You knew this would happen. You did the math. You understood the time dilation. You sat in a briefing room before the mission, and someone explained to you, very carefully using charts and graphs and equations, that if you came back, everyone you knew would be dead. And you said yes anyway. Maybe you said yes because you wanted to see the galaxy. Maybe you said yes because the mission was important. Maybe you said yes because you were young and stupid and you thought you could handle it. But you said yes, you made the choice. No one forced you onto that ship. No one tricked you. You walked on board with your eyes open, knowing what the cost would be, and you paid it. And now you have to live with it. That is the thing nobody tells you about relativistic travel. It is not the engineering that kills you. It is not the radiation or the fuel requirements or the interstellar dust. It is the fact that you survive, you make the journey, you come back, and you spend the rest of your life living in a world that is not yours, surrounded by people who are not your people, mourning a past that no one else remembers. There is a term for this in psychology: chronic temporal dislocation. It is not an official diagnosis because no one has ever actually experienced it. But researchers who study the psychological impacts of long-duration space travel have started thinking about what it would do to a person. The symptoms would probably look like a combination of extreme homesickness, survivor guilt, and a kind of existential grief that has no cure. Homesickness because you miss a place that no longer exists. Survivor guilt because everyone you knew died while you were away, and some part of you feels responsible for not being there. Existential grief because the world you understood, the framework of meaning you built your identity around, is gone, and nothing has replaced it. You are not just grieving individuals, you are grieving an entire civilization, a whole way of life, the death of context. And grief is supposed to fade with time. But how do you process grief when the thing you are grieving has been gone for 100,000 years? How do you move on when moving on means accepting that you will never go home? Some mission planners have suggested sending crews in groups. If you are going to strand people in the future, at least strand them together. That way they have someone to talk to. Someone who remembers the same world they do. Someone who speaks the same language. It is a kind of lifeboat, a tiny fragment of the past, preserved inside a crew of 5 or 10 or 20 people who are all displaced together. That helps. Maybe. But it also means everyone on board is dealing with the same trauma. You do not have anyone to lean on who is not also falling apart. And eventually the crew will age and die, and then you are alone again, unless you had children. Some proposals include raising families on board the ship during the journey. That way the mission becomes multi-generational, even if the trip itself only lasts a single human lifetime. The children grow up on the ship. They never knew Earth. They have no attachment to the world their parents left behind. When the ship arrives at its destination, or when it returns, the children are the ones who integrate. They are the ones who adapt. They are the ones who build new lives in the new era. The parents, the original crew, become the elders, the keepers of history, the ones who remember a time no one else cares about. It is a role, it is something, but it is not the life you thought you were signing up for. There is another option. Do not come back. If the cost of returning is losing everyone and everything you ever cared about, then do not return. Stay at your destination. Build a colony. Start over. Raise the next generation in a place where they are not haunted by the ghost of a dead world. That is probably the more psychologically healthy choice. It is also a harder choice because it means accepting, before you even leave, that you will never see Earth again. Not just never see it the way it was, never see it at all. You are not taking a trip, you are emigrating, permanently, one way, no round-trip ticket. Some people can do that. Humans have been emigrating to new continents and new countries for as long as humans have existed. But emigrating across space is different from emigrating across an ocean. When Europeans sailed to the Americas, they knew they might never see Europe again. But Europe was still there. If their children wanted to go back, they could. If their grandchildren wanted to visit, they could. The place still existed. It had just moved out of reach. When you leave Earth on a relativistic starship, Earth stops existing in any form you would recognize within a few thousand years. You are not emigrating to another place. You are emigrating to another time, and there is no going back, because back is not a location, it is a when, and that when is gone. So why would anyone do this? Why would anyone volunteer for a mission that guarantees you will lose everything? The answer is probably the same reason people have always done dangerous, stupid things. Because it matters. Because someone has to. Because the thing you are trying to accomplish is worth the cost. The first humans who left Africa and walked across Asia and Europe and eventually the Bering Land Bridge into the Americas did not have maps. They did not have supplies. They did not have a plan. They just walked. And most of them died. But some of them made it, and their descendants populated the entire planet. The cost was enormous. The mortality rate was horrific. But the result was that humanity spread across the globe and became the most widely distributed large mammal on Earth. If we ever spread across the galaxy, it will be the same. The cost will be enormous. The people who go will lose everything. Most of them will die. Some of them will succeed, and their descendants will look back and call them pioneers, heroes, the ones who made it possible. The original crew will not be around to hear it. They will be long dead, but maybe that is enough. Maybe knowing that your sacrifice mattered, even if no one remembers your name, is enough. Maybe it is not. That is a question every crew member has to answer for themselves before they get on the ship. And then there is the possibility, small but real, that when you get back, someone will be waiting. Not someone you knew, not someone who remembers you, but someone who knows you are coming. Because you sent a message ahead. Light travels at light speed. Your ship travels at 99.9999% of light speed. You are almost keeping pace with your own signal, but not quite. If you broadcast a message the moment you leave, that message will arrive at your destination slightly before you do. And if you broadcast a message the moment you leave your destination to return home, that message will arrive at Earth slightly before you do. It will not give much warning. A few months maybe, a few years at most, but it is something. It means Earth will know you are coming. They will have time to prepare, time to assemble a team of historians and linguists who can help you integrate, time to set up a quarantine facility because you are carrying bacteria and viruses from 100,000 years ago that no modern immune system has ever seen. Time to decide whether they even want you to land, because that is a real question. You are a contaminant, a biological time capsule full of ancient pathogens. You might be carrying plagues that modern humanity eradicated 50,000 years ago. You are also a historical treasure, a living witness to an era that no one alive has any direct knowledge of. You are dangerous and valuable in equal measure. And the people on the ground, whoever they are, will have to decide whether the risk is worth the reward. Assuming they let you land, you will spend the rest of your life being studied. You are not a person anymore. You are a data point, a primary source. Historians will want to interview you. Linguists will want to record your speech. Biologists will want samples of your gut microbiome. Anthropologists will want to document every detail of your culture, your habits, your memories. You will spend decades sitting in rooms answering questions about a world no one else remembers, and at some point you will realize that you are not helping them understand the past. You are helping them catalog it. You are a specimen, an exhibit, and when you die, they will probably put your body in a museum. Not because they are cruel, because you are irreplaceable. You are the last human from your century, the last speaker of your language, the last person who remembers what the sky looked like before whatever happened next. When you are gone, that knowledge is gone. So they will preserve you, freeze your brain maybe. Scan your connectome if the technology exists. Try to extract every last piece of information you carry before it is lost forever. You will not get to rest. You will not get to fade into obscurity. You will be remembered, studied, picked apart forever. That is the other edge of the sword. You wanted to matter. You wanted to do something significant. You got your wish. You will be remembered longer than almost anyone else in history. But you will be remembered as a curiosity, a relic, not as a person, not as someone who lived and loved and had hopes and dreams and a favorite song. As the person who came back from the past. That is your legacy. That is what you bought with 100,000 years. And maybe that is fine. Maybe being remembered at all, in any form, is better than being forgotten. Or maybe it is not. Maybe dying quietly among people who knew you and cared about you is worth more than being immortalized as a footnote in a history book. That is another question you do not get to answer until it is too late. And through all of this there is one constant. The universe did not stop while you were gone. The galaxy kept spinning, stars kept burning, planets kept orbiting, the cosmic background radiation kept cooling. Dark energy kept pushing space apart, and that expansion, that slow, steady stretching of the universe is still happening. It never stops. It cannot stop. And the farther out you travel, the more you will notice that the universe is not just big, it is getting bigger, faster, accelerating. The space between galaxies is growing, and at some point, if you go far enough, the expansion becomes faster than light. Not locally. Locally, nothing moves faster than light. But on cosmic scales, space itself can expand faster than light can cross it. And when that happens, there are places in the universe you can never reach. Not because they are too far, because they are moving away from you faster than you can ever catch up. No matter how fast your ship goes, no matter how much time dilation you experience, the destination is receding. And eventually it will cross a horizon beyond which no signal, no ship, no information of any kind can ever reach you again. That is the invisible wall, the edge of the reachable universe, and it is getting closer. And through all of this, there is one constant. The universe did not stop while you were gone. The galaxy kept spinning. Stars kept burning, planets kept orbiting. The cosmic background radiation kept cooling, dark energy kept pushing space apart, and that expansion, that slow, steady stretching of the universe, is still happening. It never stops. It cannot stop. And the farther out you travel, the more you will notice that the universe is not just big, it is getting bigger, faster, accelerating. The space between galaxies is growing, and at some point, if you go far enough, the expansion becomes faster than light. Not locally. Locally, nothing moves faster than light. But on cosmic scales, space itself can expand faster than light can cross it. And when that happens, there are places in the universe you can never reach, not because they are too far, because they are moving away from you faster than you can ever catch up. No matter how fast your ship goes, no matter how much time dilation you experience, the destination is receding. And eventually it will cross a horizon beyond which no signal, no ship, no information of any kind can ever reach you again. That is the invisible wall, the edge of the reachable universe, and it is getting closer. Most people think the universe is just sitting there, stars scattered through space like lights on a Christmas tree, static and permanent. Maybe the stars are moving a little, orbiting around galaxies, galaxies drifting slowly through the void, but the overall structure staying more or less the same. That is not what is happening. The universe is not static. It has never been static. Since the moment of the Big Bang, space itself has been expanding. Not expanding into anything, just expanding. The distance between any 2 points that are not gravitationally bound together is increasing. Every second, the universe gets a little bigger. And the implications of that fact, once you sit with them long enough, are staggering. The first person to notice this was Edwin Hubble, working at the Mount Wilson Observatory in California in the 1920s. Hubble was measuring the light from distant galaxies using the largest telescope in the world at the time, a 100-inch reflector perched on a mountain above Los Angeles. He was looking at spectral lines, the characteristic patterns of light emitted by specific elements. Hydrogen emits light at a very specific wavelength. So does helium, so does every other element. These spectral lines are like fingerprints. You can identify what a star is made of just by looking at the pattern of lines in its spectrum. Hubble noticed something strange. The spectral lines from distant galaxies were shifted toward the red end of the spectrum. Not a little, a lot, and the farther away the galaxy was, the more the lines were shifted. This is called redshift. It happens when the source of light is moving away from you. Same principle as the Doppler effect with sound. When an ambulance drives toward you, the siren sounds higher pitched because the sound waves are compressed. When it drives away, the siren sounds lower because the waves are stretched. Light does the same thing. If a galaxy is moving away from you, its light gets stretched, shifting toward longer wavelengths, toward the red end of the spectrum. Hubble measured the redshifts of dozens of galaxies and plotted them against their distances. The result was a straight line. The farther away a galaxy was, the faster it was moving away. This is now called Hubble's law. The recession velocity of a galaxy is proportional to its distance. The formula is simple. Velocity equals Hubble constant times distance, or written out, v equals h0 times d. The Hubble constant is just a number that tells you how fast the expansion is happening. Today we measure it at about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are moving away from us about 70 kilometers per second faster. That does not sound like much. 70 kilometers per second is fast by human standards, but it is a tiny fraction of the speed of light. Except the effect stacks. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away, about 3 billion light-years distant, is receding at 70,000 kilometers per second. That is almost a quarter of the speed of light, and it just keeps going. Hubble did not know what was causing this. He reported the observation, published the data, and the rest of the physics community spent the next decade arguing about what it meant. Some thought the galaxies were literally flying apart, that the Big Bang had been an explosion in space and everything was still coasting outward from the blast. Others, including Einstein after he finally accepted the evidence, realized that space itself was expanding. The galaxies are not moving through space, they are embedded in space, and the space between them is growing. Think of it like raisins in a rising loaf of bread. The dough expands as it bakes, and the raisins move apart, but the raisins themselves are not moving through the dough. The dough is expanding and carrying them along. That is what is happening to galaxies. Space is the dough. Galaxies are the raisins. And the oven is the universe, still baking, still expanding, still stretching the dough thinner and thinner with every passing second. For most of the 20th century, cosmologists assumed the expansion was slowing down. Gravity pulls everything together. The universe is full of matter. That matter exerts a gravitational pull on everything around it. So logically, the expansion should be decelerating, maybe slowly. Maybe so slowly you could not measure it, but decelerating. That was the assumption. The question was whether the expansion was slowing down fast enough that gravity would eventually win, stop the expansion, and pull everything back together in a big crunch. Or whether the expansion was slowing down but not fast enough, so the universe would keep expanding forever, just at an ever-decreasing rate, asymptotically approaching some final coasting speed. Either way, the expectation was deceleration. The universe was supposed to be slowing down. In 1998, two independent teams of astronomers set out to measure how fast the deceleration was happening. They were looking at Type 1a supernovae, a specific kind of exploding star that always blows up with roughly the same brightness. These supernovae are useful because they act like cosmic mile markers. You can measure how bright they appear, compare that to how bright they actually are, and calculate how far away they are. Then you measure their redshift, which tells you how fast they are receding. Do this for enough supernovae at different distances, and you can map out the expansion history of the universe. You can see whether the expansion was faster in the past and has been slowing down since, or whether something else is going on. Both teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory and the other led by Brian Schmidt and Adam Rice, found the same thing. The distant supernovae, the ones whose light had been traveling for billions of years, were dimmer than they should have been. Not because they were farther away than expected, because they were farther away than they should have been for their redshift. The universe had not been decelerating. It had been accelerating. The expansion was speeding up. That result made no sense. Gravity pulls things together. It does not push them apart. If the universe is full of matter and matter exerts gravity, the expansion should be slowing down. The only way the expansion could be speeding up is if there is something else, something that does not pull but pushes, something with negative pressure, something that acts like anti-gravity. The teams called it dark energy because they had no idea what it was, and it did not emit light. The name stuck. Dark energy is now understood to be the dominant component of the universe. Roughly 68% of the total energy density of the cosmos is dark energy. About 27% is dark matter, the invisible stuff that holds galaxies together. And only about 5% is ordinary matter, the stuff we are made of. The stuff stars are made of, the stuff we can see. We are the minority. The universe is mostly invisible, and most of that invisible stuff is pushing space apart. Dark energy does not clump. It does not form structures. It does not interact with light or matter in any way we can detect, except through its gravitational effect. It is spread uniformly throughout space, and its density does not change as the universe expands. That last part is critical. Normal matter gets diluted as the universe expands. If you have a certain amount of matter in a box and the box doubles in size, the density of matter drops by half. Dark energy does not behave that way. As space expands, more dark energy appears. The density stays constant, which means the total amount of dark energy in the universe is increasing over time. And because dark energy pushes, the more of it there is, the faster the expansion accelerates. This is a runaway process. The expansion creates more space. More space means more dark energy. More dark energy means faster expansion. Faster expansion means even more space. The loop feeds itself, and there is no break. What that means for interstellar travel is that the universe has a speed limit, and it is not the speed of light. The speed limit is the rate of expansion, and in the regions of space where expansion is happening faster than light can travel, no ship, no signal, no information of any kind can ever cross that boundary. This is not a violation of relativity. Special relativity says nothing with mass can move through space faster than light. It does not say anything about space itself expanding faster than light. Space is not a thing. It is not made of particles. It does not have mass. It is just the geometry that things exist in. And that geometry can stretch as fast as it wants. There is no rule against it. So at large enough distances, the expansion wins. The space between you and a distant galaxy is growing faster than light can cross it, which means light leaving that galaxy will never reach you, not because it is moving too slowly, because the finish line is receding faster than the light can run. Astronomers call this the cosmological horizon. It is similar to the particle horizon, which is the boundary of the observable universe, but they are not the same thing. The particle horizon is determined by how far light has had time to travel since the Big Bang. The universe is about 13.8 billion years old. Light has been traveling for 13.8 billion years. So the farthest we can see, in principle, is about 13.8 billion light years away. Except space has been expanding the whole time, so the actual distance to the objects we are seeing is much larger. The most distant objects we can see today are about 46 billion light-years away. Their light has been traveling for nearly the entire age of the universe, but the space between us and them has stretched so much during that time that they are now much farther away than 46 billion light-years in moving coordinates. That is the particle horizon. It is the edge of what is observable. The cosmological horizon is different. It is the edge of what is reachable. Even if you could travel at the speed of light, there are places in the universe you could leave right now and never arrive at, because the space between you and them is expanding faster than you can cross it. And because the expansion is accelerating, that horizon is shrinking. There are galaxies we can see today that we could theoretically reach if we left right now at light speed. But if we wait too long, they will cross the horizon. They will slip beyond the boundary. And once they do, no amount of speed will ever get us there. The universe is not just big, it is pulling itself apart. And the farther away something is, the faster it is being pulled. Here is a concrete example. The Andromeda Galaxy is about 2.5 million light-years away. It is the nearest large galaxy to the Milky Way, and it is moving toward us, not away. Andromeda and the Milky Way are gravitationally bound. They are close enough that their mutual gravity is stronger than the expansion of space between them. In about 4.5 billion years, the two galaxies will collide. So Andromeda is not receding, it is approaching. But most galaxies are not like Andromeda. Most galaxies are far enough away that the expansion dominates. Take a galaxy 10 million light-years away. The expansion is carrying it away from us at about 200 kilometers per second. That is slow compared to the speed of light, which is about 300,000 kilometers per second. So you could still catch that galaxy if you had a ship that could travel at light speed. You would need to account for the fact that the galaxy is moving, so you would need to aim ahead of where it is now, like leading a target. But you could get there. Now take a galaxy 1 billion light-years away. It is receding at about 20,000 kilometers per second, still less than light speed. Still reachable in theory, if you could sustain light-speed travel for long enough. But now take a galaxy 10 billion light-years away. It is receding at about 200,000 kilometers per second. That is 2/3 the speed of light. You could still catch it if you left now and traveled at light speed, but the margin is narrowing. And if you take a galaxy 14 billion light-years away, it is receding faster than light. Space between us and that galaxy is expanding so fast that even a beam of light we fire in its direction today will never reach it. The light will travel forward, covering 300,000 kilometers every second, but the space it is traveling through is stretching faster than that. The light makes progress, but the destination keeps moving away faster than the light can close the gap. It is like running on a treadmill that is accelerating faster than you can run. You are moving forward relative to the treadmill belt, but the belt is pulling you backward faster than you are running forward. You never reach the front of the treadmill. You just stay in place or drift backward. That is what happens to light traveling through expanding space. It moves forward through space, but space itself is expanding behind it faster than it is moving forward, so the total distance between the light and its destination grows instead of shrinking. This is not hypothetical. We can see galaxies that are already beyond the cosmological horizon. We can see them because the light we are receiving left those galaxies billions of years ago, back when they were closer, and the expansion had not yet carried them beyond the horizon. The light has been traveling toward us the whole time, and during that journey, the galaxy it came from crossed the threshold and is now unreachable. We are seeing the past. We are seeing the galaxy as it was when it was still within the reachable universe, but the galaxy as it exists today, right now at this moment, is gone, not destroyed, just unreachable. If we pointed a telescope at that spot in the sky and waited, we would keep seeing light from that galaxy for a while longer, because there is still light in transit, but eventually the light will run out. The last photon that will ever reach us from that galaxy will arrive, and after that the galaxy will disappear from view. It will fade from the observable universe, not because it stopped shining, because the space between us and it has stretched so much that no new light from it can ever reach us. And this is happening to more and more galaxies every day. The cosmological horizon is contracting. The reachable universe is shrinking. Right now, as you are reading this, there are galaxies slipping across the boundary, passing from the category of places we could theoretically visit into the category of places that are forever out of reach, and there is nothing we can do about it. This is not an engineering problem. It is not a fuel problem. It is not a question of building a faster ship or finding a better propulsion system. The boundary is set by the structure of space-time itself. Dark energy is built into the fabric of the cosmos. It is not something you can turn off or avoid or route around. It is everywhere, it affects everything, and it is winning. Gravity holds local structures together. Galaxies stay gravitationally bound. Galaxy clusters stay bound, but on scales larger than a few 100 million light-years, gravity loses. Expansion dominates, and the larger the scale, the more dominant expansion becomes. Eventually, every galaxy cluster that is not already gravitationally bound to our local group will drift beyond the horizon. Eventually, the only galaxies we will be able to see will be the ones in our immediate neighborhood. Andromeda, the Triangulum galaxy, a few dozen smaller dwarf galaxies, everything else will be gone, receded into the unreachable dark. This will take trillions of years. The process is slow, but it is inevitable. So what does that mean for a starship? It means you need to pick your destination carefully. If you want to visit a galaxy outside the local group, you need to leave soon. Not soon as in next year. Soon as in the next few 100 million years. After that, Depending on how far away the galaxy is, it might cross the horizon, and once it crosses, you have missed your chance forever. No future generation will ever get another shot. The destination will still exist. It will still have stars and planets, and maybe even civilizations, but it will be causally disconnected from us. It will be in a region of the universe that we can never send a signal to, never receive a signal from, never visit, never interact with in any way. It might as well not exist. For all practical purposes, it is outside our universe. The universe we can interact with is smaller than the universe that exists, and it is getting smaller. That is the invisible wall, not a barrier made of matter or energy, a barrier made of geometry, a boundary written into the expansion rate of space, and it surrounds us on all sides, tightening slowly, inexorably, cutting us off from more and more of the cosmos with every passing eon. People do not like thinking about this. It is uncomfortable. We are used to thinking of the universe as a place we can explore, at least in principle. We imagine future civilizations spreading across the galaxy, sending probes to distant stars, maybe even traveling to other galaxies millions of years from now. And some of that is still possible. The Milky Way is not expanding. The local group of galaxies is not expanding. We have tens of billions of years before the Sun dies, and even longer before the galaxies in our local group finish merging into a single giant elliptical galaxy. There is time, there is room, but the universe beyond our local group is slipping away. And eventually, if you are standing on a planet in that far future, looking up at the night sky, you will not see a sky full of galaxies. You will see a handful of nearby galaxies, all gravitationally bound to you, and beyond them, nothing, just darkness. The cosmic microwave background will have redshifted into invisibility. The distant galaxies will have faded from view. The sky will be emptier than it has ever been. And any astronomers living at that time, if there are any, will look at the universe and conclude that they live in a small island of matter surrounded by infinite empty space. They will have no evidence that the universe was ever any different, no evidence of the Big Bang, no evidence of cosmic expansion, no evidence that billions of other galaxies ever existed. All of that information will have been erased by the expansion. The cosmological horizon will have contracted so far that the observable universe will contain only the local structures, and unless someone left them a message, a detailed archive of what the universe looked like back when it was young and full of galaxies, they will never know. They will look up at the sky and think they are alone, and they will be wrong, but they will have no way to prove it. That is what dark energy does. It does not just push galaxies apart, it erases the past, it deletes information. It takes a universe that was once connected, where in principle every part could communicate with every other part, and it cuts those connections. It partitions the cosmos into isolated regions that can never again interact. And within each region, the evidence of the other regions slowly fades until it is gone completely. This is not a distant future problem. This is already happening. There are galaxies we can see in our telescopes today whose light left them so long ago that by the time we see them, they have already crossed the horizon. We are looking at their ghosts. The light is real. It traveled for billions of years to reach us. But the galaxy it came from is no longer in our reachable universe. If we launched a probe today aimed at that galaxy, the probe would never arrive. It would travel outward for billions of years, covering vast distances, and the galaxy would just keep receding. The probe would eventually run out of fuel or break down or be destroyed by radiation or micrometeoroids, and it would drift through the expanding void forever, never reaching its target, because the target is moving away faster than the probe can travel. That is the trap. That is the prison. Space itself is the bars. And the worst part is, We only figured this out 25 years ago. For most of human history, we did not know the universe was expanding. For most of the 20th century, we thought it was expanding but slowing down. It was not until 1998, less than 3 decades ago, that we discovered the expansion is accelerating. We have known about dark energy for 1 human generation, and already it has reshaped our understanding of the cosmos. We now know that the universe has an expiration date, not in the sense that it will end, but in the sense that most of it will become permanently inaccessible. We are living in a brief window of cosmic history where the universe is both old enough to have formed galaxies and stars and planets, and young enough that we can still see most of it. A few trillion years from now, that window will have closed. The universe will still be here, but most of it will be hidden behind the horizon, forever out of reach, forever invisible, as if it never existed. We are the lucky ones. We are alive at a time when the universe is still mostly visible, when we can still look out with our telescopes and see the vast sweep of cosmic history written in the light of distant galaxies. That will not always be true. And if we want to visit those distant places, if we want to send probes or messages or ships to the far corners of the cosmos, we need to do it now. Not literally now, but soon, cosmically soon, while the destinations are still reachable, before the invisible wall closes in, before the universe locks us out of itself and throws away the key. That is the limit dark energy imposes, not a limit on how fast we can go, a limit on where we can go, a shrinking bubble of reachable space, surrounded by an ever-growing ocean of the unreachable, and every second the bubble gets smaller. Every second more destinations slip across the boundary into the forever inaccessible. We are not running out of time. We are running out of universe. And no amount of clever engineering or relativistic time dilation will change that. Because the wall is not made of matter, it is made of space, and space is expanding, and there is no way to stop it. We are running out of targets. That sentence should not be true. The universe is enormous. Hundreds of billions of galaxies scattered across observable space, each one containing hundreds of billions of stars. There is more stuff out there than we could visit in 1 trillion lifetimes. The problem is not that we are running out of places to go. The problem is that the places are running out on us. They are slipping across a boundary we cannot see, crossing a line drawn by the expansion of space itself, and once they cross it, they are gone, not destroyed, not hidden, just unreachable, forever. No matter how fast we build our ships, no matter how close to light speed we push them, there are destinations that were theoretically accessible yesterday that will not be accessible tomorrow. And the list of doomed targets is growing. Every second, more galaxies slip across the cosmological horizon into permanent exile. We are living through the closing of a window, and most people do not even know the window exists. Here is how it works. The universe is expanding. We covered that. Dark energy is accelerating the expansion. We covered that too. What we have not covered is the practical consequence of that acceleration for anyone who actually wants to travel somewhere. The consequence is this. There is a set of objects in the universe, galaxies mostly, that you could reach if you left right now at light speed. Call that set the reachable universe. Everything inside that set is a valid destination. Everything outside it is not. The boundary of that set is the cosmological horizon. Now here is the part that makes this a crisis, instead of just an interesting fact. The reachable universe is shrinking. The cosmological horizon is not sitting still. It is contracting, moving inward, getting closer. Every year the boundary moves a little closer to us and a little farther from the distant galaxies on the other side. which means galaxies that were inside the reachable set last year are outside it this year. They have crossed the line, they have become unreachable, and they are never coming back. Let us put numbers on this because the numbers are what make it real. Right now, today, the cosmological horizon sits at about 16 billion light-years from Earth. That is the comoving distance, which accounts for how much space has expanded during the time the light was traveling. Anything closer than 16 billion light-years is in principle reachable. Anything farther is not. If you launched a probe today at light speed aimed at a galaxy 17 billion light-years away, the probe would never get there. It would travel outward forever, covering 300,000 kilometers every second, and the distance between the probe and the galaxy would still grow. The galaxy is receding faster than light can close the gap. The probe would spend eternity chasing a target it can never catch. Now, 16 billion light-years sounds like a lot of room, and it is. The vast majority of galaxies we can currently see are still within the reachable zone, but the zone is shrinking fast. Over the next 100 billion years, the cosmological horizon will contract from 16 billion light-years down to about 5 billion light-years. That is a loss of 2/3 of the reachable universe. 2 out of every 3 galaxies that are currently reachable will slip beyond the horizon during that time, and there is nothing we can do to stop it. The math is straightforward. The rate of expansion is set by the Hubble constant, about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance, space is expanding at 70 kilometers per second. That rate is not changing much locally, but the total expansion rate between you and a distant galaxy depends on how much space there is between you and that galaxy. More space means more expansion, which means the farther away something is, the faster it is receding. At a distance of about 14 billion light-years, the recession velocity equals the speed of light. Beyond that distance, galaxies are receding faster than light. Space between us and them is expanding faster than light can cross it. And because the expansion is accelerating, that boundary is moving closer. A galaxy that is 15 billion light-years away right now is receding faster than light. But 1 billion years ago, it was closer, and it was receding slower. It was inside the reachable zone. If someone had launched a light-speed probe back then, the probe could have eventually reached it, but no one did. And now it is too late. The galaxy has crossed the threshold. It is gone. Here is a specific example. The galaxy GNZ11 is one of the most distant galaxies ever observed. It sits at a distance of about 32 billion light-years in comoving coordinates. The light we see from it today left the galaxy when the universe was only 400 million years old. That light has been traveling for over 13 billion years. But the galaxy itself, as it exists right now, is much farther away than it was when the light left. Space has been expanding the whole time. GNZ11 is receding from us at about 2.3 times the speed of light. It is far beyond the cosmological horizon. It is unreachable. It has always been unreachable. We can see it because we are looking at old light, light that left the galaxy back when it was closer. But the galaxy as it exists today is in a part of the universe we will never be able to visit. If we aimed a probe at GNZ11 and launched it at light speed, the probe would travel for trillions of years and never arrive. The target is moving away faster than the probe can catch up. The distance between the probe and the galaxy would grow, not shrink. The probe would make forward progress through space, but space itself would be expanding behind it faster than it is moving forward. It is like trying to swim against a current that is faster than you can swim. You move forward relative to the water, but the water is moving backward faster than you are moving forward. so you drift backward relative to the shore. That is what happens when you try to reach a galaxy beyond the cosmological horizon. You move forward through space. Space moves backward faster. You lose. But GNZ 11 was never reachable. It was born beyond the horizon. The tragedy is not losing access to something we never had. The tragedy is losing access to things we could have reached. Take the Virgo cluster. It is a massive collection of galaxies about 54 million light-years away. It contains over 1,000 galaxies. It is one of the largest structures in our local region of the universe. And it is receding from us at about 1,200 kilometers per second due to the expansion of space. That is about 0.4% of the speed of light. Slow enough that the Virgo cluster is well within the reachable zone. If we launched a probe today at light speed, it could reach the Virgo cluster in about 54 million years. Not fast by human standards, but feasible on cosmic timescales. The Virgo cluster is reachable. It will stay reachable for a long time, but not forever. Eventually, the accelerating expansion will carry it far enough away that even light cannot catch it. The cluster will cross the cosmological horizon, and once it does, it is gone. We lose access permanently. The timeline for when that happens depends on how fast the expansion accelerates. Current models suggest that the Virgo cluster will remain reachable for at least a few trillion years. That is a long time. Long enough that we do not need to panic about losing access anytime soon. But the clock is ticking. And for more distant structures, the clock is ticking much faster. Take the Coma cluster. It is about 300 million light-years away. It contains over 1,000 galaxies. It is receding at about 7,000 kilometers per second, a bit over 2% of light speed. Still reachable, still within the zone, but the margin is smaller. The Coma cluster will cross the horizon much sooner than Virgo. Maybe a few 100 billion years from now. Still a long time, but not infinite. And for clusters farther out, the timelines get shorter. A cluster 1 billion light-years away might only remain reachable for another 100 billion years or so. After that, it slips across the boundary and disappears from the reachable universe. And we are talking about clusters here, huge structures containing thousands of galaxies each. Every time a cluster crosses the horizon, we lose access to thousands of galaxies all at once. The reachable universe is not just shrinking, it is collapsing. Entire regions of space are being cut off, walled off by the expansion, locked behind a barrier that no amount of speed or technology can overcome. And it gets worse, because even the galaxies that stay within the reachable zone, even the ones that never cross the horizon, are getting harder to reach over time. The longer you wait, the farther away they are, and the longer the trip takes. Suppose you want to visit a galaxy that is currently 1 billion light-years away. If you leave today at light speed, the trip takes longer than 1 billion years because the galaxy is moving away while you are traveling toward it. You have to cover not just the initial distance but also the additional distance that accumulates while you are in transit. The actual travel time ends up being longer than the initial light travel time. How much longer depends on the recession velocity. For nearby galaxies, the difference is small. For distant galaxies, the difference is huge. A galaxy 1 billion light-years away might take 2 billion years to reach even at light speed, because by the time you get there, it has moved. And if you wait 1 billion years before launching your probe, the galaxy is now farther away. It has receded during the time you were sitting around deciding whether to go. Now the trip takes even longer. Wait another 1 billion years and the trip takes even longer still. Eventually, if you wait too long, the galaxy crosses the horizon and becomes unreachable no matter when you launch. There is a deadline, a point of no return, and it is not fixed. It depends on when you leave. The sooner you go, the more destinations remain accessible. The longer you wait, the fewer options you have. This creates a kind of cosmic triage. If you are a civilization that wants to explore the universe, you have to prioritize. You have to decide which destinations matter most and visit them first, because if you wait, they might be gone, not destroyed, not dead, just out of reach. Suppose you are planning missions to 10 different galaxy clusters. 5 of them are relatively close, 5 of them are far away. The close ones will remain reachable for trillions of years. The distant ones will cross the horizon in a few 100 billion years. If you visit the close ones first, you might lose access to the distant ones before you get around to them. If you visit the distant ones first, you can always go back and visit the close ones later. The rational strategy is to prioritize the targets with the shortest expiration dates. Visit the things that are about to slip away before they slip away. That is triage. That is resource allocation under constraints. And the constraint is time, cosmic time. The expansion is not waiting for you to figure out propulsion systems or build starships or decide whether the trip is worth it. The expansion is happening now. The horizon is contracting now. Destinations are crossing the threshold now. Every year you delay is a year less you have to reach the things that are about to become unreachable. Now, a few 100 billion years sounds like an absurdly long time. It is. Humanity has only existed for a few 100,000 years. Recorded history is a few thousand years old. 100 billion years is tens of thousands of times longer than the entire span of human civilization. So why does this matter? Why should anyone care about losing access to distant galaxies on timescales that dwarf the age of our species? Because if we are serious about being a spacefaring civilization, if we are serious about exploring the universe, we have to think in cosmic timescales. We have to think in terms of millions of years, billions of years, trillions of years. We have to plan for a future that extends far beyond the lifespan of our sun, far beyond the lifespan of our planet, far beyond the lifespan of our species as it currently exists. And if we are thinking in those terms, then losing access to 2/3 of the reachable universe over the next 100 billion years is not a distant abstract problem. It is a present crisis. It is a countdown, and it is already running. There is also the question of what counts as nearby. Right now we think of the local group, our cluster of galaxies, as our immediate neighborhood. It includes the Milky Way, Andromeda, the Triangulum Galaxy, and a few dozen smaller dwarf galaxies. All of them are gravitationally bound to each other. The expansion of space is not pulling them apart because gravity is holding them together. The local group is safe. It will never cross the cosmological horizon because it is not receding. It is our home. But the local group is small. It spans about 10 million light-years across. That is a tiny patch of the universe. Beyond the local group, the next nearest large structure is the Virgo cluster, 54 million light-years away. And beyond that, everything else. The Coma cluster, the Hercules cluster, the Shapley supercluster, the Laniakea supercluster, a massive structure spanning 500 million light-years that includes the Virgo cluster and the local group as tiny subclusters. All of these structures are receding, all of them are subject to the expansion, and all of them will eventually cross the horizon if the expansion continues accelerating. When that happens, the reachable universe will have shrunk down to just the local group. Everything beyond our immediate neighborhood will be gone, and anyone alive at that time will look up at the sky and see a handful of nearby galaxies, all bound to each other, and beyond them, nothing. Darkness, empty space stretching out to infinity, no distant galaxies, no galaxy clusters, no large-scale structure, just a small island of matter surrounded by a void. That is the future. That is where the expansion is taking us, not tomorrow, not in a million years, but eventually, inevitably. And here is the thing that makes this truly strange. The galaxies that cross the horizon do not disappear instantly, they fade. You can still see them for a while after they become unreachable, because the light that left them before they crossed the horizon is still in transit. That light is still traveling toward you. It will keep arriving for a long time, maybe billions of years, depending on how far away the galaxy was when it crossed. But eventually, the last photon will arrive. The last bit of light that will ever reach you from that galaxy will hit your telescope, and after that, nothing. No more light, no more information. The galaxy goes dark, not because it stopped shining, because the light it is emitting now can no longer reach you. Space between you and it is expanding too fast. The photons are still being emitted. They are still traveling through space at 300,000 kilometers per second. But the space they are traveling through is stretching faster than they can cross it, so they never arrive. They just drift through the expanding void forever, covering vast distances, never reaching their destination. And from your perspective, the galaxy fades to black. It disappears from the sky, not because it died, because the universe pulled it beyond the edge of what you can see. This creates a distinction between the observable universe and the reachable universe. The observable universe is the set of all objects whose light can currently reach us. It includes everything out to about 46 billion light-years away in co-moving coordinates. That is the particle horizon. It is set by how long light has had to travel since the Big Bang. The reachable universe is the set of all objects we could theoretically reach if we left right now at light speed. It includes everything out to about 16 billion light-years away. That is the cosmological horizon. It is set by the expansion rate and the acceleration of that expansion. The observable universe is bigger than the reachable universe. There are objects we can see that we can never visit. We are receiving light from galaxies that are already beyond the cosmological horizon, already unreachable, already lost. We are looking at ghosts, echoes of a universe that used to be connected to us but is not anymore. The light is real. The journey the light made was real, but the galaxy it came from is no longer in a part of the universe we can interact with. We are seeing the past, a past where that galaxy was closer, a past where the expansion had not yet carried it beyond the threshold, but the present, the now, is different. In the present, that galaxy is gone, and both horizons are moving. The particle horizon is expanding, slowly. Because light keeps traveling and the universe keeps aging, we can see farther and farther back in time. New light from distant objects keeps arriving. But the rate at which the observable universe is growing is slowing down because the expansion is accelerating. Eventually, the observable universe will stop growing. No new objects will come into view, and then it will start shrinking. Objects at the far edge of the observable universe will cross the particle horizon in reverse. Their light will redshift into invisibility. They will fade from view, not because they stopped emitting light, because the space between us and them has stretched so much that the light has been redshifted down to wavelengths we can no longer detect. The photons arrive, but they arrive as radio waves with wavelengths longer than the size of a galaxy, undetectable, useless, effectively gone. The cosmological horizon, meanwhile, is contracting. It is moving inward, getting closer to us, cutting off more and more of the universe from the reachable set. At some point, far in the future, the two horizons will converge. The observable universe and the reachable universe will be the same size. Everything you can see will be something you could theoretically reach, and everything beyond that will be both invisible and unreachable, completely disconnected, causally separated, as if it exists in a different universe entirely. Now imagine you are a civilization 1 trillion years from now. You have survived the death of your star. You have moved to a new star. Or maybe you have learned to harvest energy from black holes or some other exotic source. You are still around. You are still exploring. You look up at the sky and you see the local group, a few dozen galaxies. That is it. That is the entire universe as far as you are concerned. You have no evidence that anything else exists. The cosmic microwave background has redshifted into invisibility. You cannot detect it anymore. The distant galaxies have faded. You cannot see them. Your telescopes show you a small cluster of gravitationally bound galaxies, and beyond them, nothing, just darkness. You run the equations of general relativity. You try to figure out the structure of the universe, and you conclude, based on the evidence available to you, that the universe is small. It contains a few dozen galaxies. It is not expanding, or if it is, the expansion is so slow you cannot measure it. You have no way to know that there used to be hundreds of billions of other galaxies out there. No way to know that the universe used to be full of light and structure and complexity. No way to know that you are living in the aftermath of a cosmic event that erased most of the universe from view. All the evidence has been deleted, redshifted away, expanded away, lost to the acceleration, unless someone left you a message. Unless some earlier civilization recorded what the universe looked like back when it was young and full of galaxies and stored that information in a format you could read 1 trillion years later, you would never know. You would look at your small island of galaxies and think you were looking at the whole universe, and you would be wrong, but you would have no way to prove it. That is what dark energy does. It does not just separate us from distant galaxies. It erases the evidence that they ever existed. It takes a universe that was once full and makes it look empty. It takes a cosmos that was once connected and breaks it into isolated fragments that can never communicate. And it does this slowly enough that no one notices it happening. The changes play out over billions or trillions of years, longer than stars live, longer than galaxies survive in their current form, longer than any civilization we can currently imagine. But the changes are cumulative. They add up, and eventually, the universe you are living in is not the universe your ancestors lived in. Not because anything in your local area changed, because everything beyond your local area disappeared. And once it disappears, it is gone. There is no getting it back. No future technology will let you visit a galaxy that has crossed the cosmological horizon. No clever trick with wormholes or warp drives or quantum tunneling will let you cheat the expansion, because the expansion is not a thing. It is not a field or a force you can push against. It is the geometry of space-time itself. It is the shape of the universe, and the shape is stretching, and there is no way to stop it. So what do we do? What is the rational response to living in a universe that is slowly erasing itself? One option is to ignore it. The timescales are so long that they do not matter to us. Humanity will be long gone before the Virgo cluster crosses the horizon. The Sun will die in 5 billion years. The Milky Way will collide with Andromeda in 4.5 billion years. The Earth will be uninhabitable in less than 1 billion years as the Sun gets hotter and boils off the oceans. We have more immediate problems. Why worry about losing access to distant galaxy clusters trillions of years from now when we might not survive the next 1,000 years? That is a fair point, but it is also short-sighted. Because if we are serious about becoming a spacefaring species, if we are serious about spreading beyond Earth and surviving for the long term, we have to think in cosmic timescales. We have to plan for futures that extend far beyond our current lifespan. And if we do that, if we take the long view, then the contraction of the reachable universe is not a distant, abstract problem. It is a constraint we have to design around. It is a deadline we have to meet, and it adds urgency to the project of exploring the cosmos. Because the longer we wait, the less of the universe remains accessible. The window is closing, and once it closes, it does not reopen. Another option is to accept it. The reachable universe is shrinking. Fine, we will explore what we can reach and forget about the rest. Focus on the local group. Focus on the nearby structures that will remain accessible for trillions of years. Let the distant galaxies go. They were never really part of our future anyway. If we cannot get there, they do not matter. That is a pragmatic response. It is also a kind of surrender. It is accepting that the universe is bigger than we will ever be able to explore. That there are places out there we will never see, never visit, never understand, because the geometry of space-time itself forbids it. And maybe that is fine. Maybe the local group is enough. Maybe a few dozen galaxies, each containing hundreds of billions of stars, each containing trillions of planets, is more than enough to keep us busy for the lifespan of the universe. Maybe we do not need to visit every galaxy. Maybe we do not need to explore every corner of the cosmos. Maybe we can be content with the small patch of it we have access to. But that feels like giving up. It feels like admitting defeat before the fight even starts. And humans do not usually respond well to being told there are places they cannot go. The third option is to take it as a challenge. The reachable universe is shrinking, so we need to move fast. We need to prioritize the distant targets. We need to build the ships, develop the technology, and launch the missions before the window closes. Because once it closes, we lose the option, we lose the chance. And losing the chance means losing a part of the universe forever. That creates a kind of existential urgency, not an immediate crisis, not a panic, but a long-term pressure. A recognition that time is finite even on cosmic scales, that the universe is not static, that the map of what is reachable today will not be the map of what is reachable tomorrow. And if we want to explore the full universe, or as much of it as physics allows, we need to start now. Not now as in this year, now as in this era, this epoch. This brief window of cosmic history where the universe is old enough to support life and young enough that most of it is still within reach, because that window is closing, slowly, inexorably. And we are the only ones who can decide whether we walk through it before it shuts. And that decision matters because the stakes are not just about seeing new places or planting flags on distant worlds. The stakes are about knowledge, about understanding, about answering the deepest questions we have about the nature of reality. Every galaxy we lose access to is a piece of the puzzle we can never examine. Every structure that crosses the horizon is a data point we can never collect. The universe is a laboratory. It is the only laboratory we have for studying cosmology, for testing our theories about the Big Bang and dark matter and dark energy and the fundamental forces. And the laboratory is shrinking. The experiments we can run in the future will be fewer and more limited than the experiments we can run today, because the universe itself is deleting the evidence, and once it is deleted, it is gone. We cannot reconstruct it. We cannot infer it. We can only guess. And guesses are not science. Science requires data, and the data is disappearing, crossing the horizon, fading into the unreachable dark. Every second we wait is a second less we have to study the cosmos in its full complexity. Every year we delay is a year closer to a future where the universe is smaller, emptier, and less knowable than it is today. That is the cost. That is the price of inaction, and it is a price that keeps compounding. So yes, we are running out of targets, not immediately, not catastrophically, but inevitably. The universe is pulling itself apart, and the parts that are being pulled away are leaving our reach, slipping beyond the boundary, vanishing into a region of space-time we will never be able to visit. And the process is accelerating. The rate at which we are losing access is increasing, which means the urgency is increasing. The window is not just closing, it is closing faster. And if we want to walk through it, if we want to explore the distant reaches of the cosmos before they become unreachable, we need to start building the ships, we need to start making the plans, we need to start moving, because the universe is not going to wait. The expansion does not care about our readiness. The cosmological horizon does not pause while we figure out propulsion systems or debate funding priorities. It just keeps contracting, cutting us off, locking doors, and every door that locks is a part of the universe we will never see, a place we will never visit, a mystery we will never solve, and once it is locked, it stays locked, forever. So here we are, 50 years to cross the galaxy at 99.999% of light speed, 100,000 years for everyone you left behind, a shrinking bubble of reachable space surrounded by an accelerating void that swallows destinations faster than we can build ships to reach them. 3 layers of walls, 3 separate prisons, each one nested inside the other, each one enforcing its own version of the word impossible. The first wall is technological. We cannot build the ship. Not yet, maybe not ever. The energy requirements are staggering. The engineering challenges are unsolved. The materials do not exist. The fuel does not exist. The propulsion systems do not exist. We have ideas. We have proposals. We have thought experiments and napkin sketches and research papers outlining what such a ship might look like if every single unsolved problem were somehow solved simultaneously. But we do not have hardware. We do not have a working prototype. We do not even have a clear path from here to there. The gap between what we can do and what we need to do is measured not in years of development, but in breakthroughs. Fundamental breakthroughs in physics, in materials science, in energy generation, in a dozen fields that are currently stuck on problems that have no obvious solutions. This is not pessimism. This is just accounting. We are trying to build a machine that accelerates to near light speed, survives the journey through a radiation-soaked interstellar medium where every hydrogen atom hits like a bullet, maintains life support for decades, and then decelerates at the other end without vaporizing everyone on board. That machine does not exist. It might never exist. The technological wall is high and it is real. The second wall is relativistic. Time dilation is not optional. It is not a feature you can disable. If you move fast enough to make interstellar travel feasible, you pay the price. The price is time. Your time runs slow. The universe outside runs fast. You cross the galaxy in 50 years of subjective experience and return to find that 100,000 years have passed on Earth. Everyone you knew is dead. Everything you cared about is gone. The civilization that built your ship has collapsed and been replaced a dozen times over. You are not returning home. You are stepping into an alien future where no one remembers your name and no one speaks your language. That is the cost. That is what relativity demands, and there is no way around it. You cannot turn time dilation off. You cannot choose to experience the journey at normal speed and still arrive within a human lifetime. The math does not allow it. If you want to cross galactic distances in less than thousands of years of ship time, you need time dilation. And if you use time dilation, you lose your present. You trade it for someone else's future. That trade is mandatory. It is written into the geometry of space-time. It is not negotiable. The third wall is cosmological. The universe is expanding. Dark energy is accelerating the expansion, and the consequence of that acceleration is that most of the universe is receding from us faster than light can travel. There is a boundary, the cosmological horizon, beyond which nothing we send will ever arrive. That boundary is not fixed. It is contracting, moving inward, cutting off more and more of the cosmos every year. Galaxies that are reachable today will not be reachable a billion years from now. Clusters that we could theoretically visit if we left right now will slip beyond the horizon if we wait too long. The universe is pulling itself apart, and the pieces that get pulled away are lost. Not destroyed, not hidden, just unreachable, forever. No amount of speed changes that. No clever engineering solves it. You cannot outrun the expansion. You cannot catch a galaxy that is receding faster than light. The cosmological wall is absolute. It is a limit imposed by the structure of the universe itself. And it is closing in. 3 walls, 3 limits, and together they define the boundaries of what is physically possible for a species like ours. We live in a universe that is vast almost beyond comprehension, filled with hundreds of billions of galaxies, each one containing hundreds of billions of stars. And yet most of that universe is off limits. Most of it will always be off limits, not because we are not clever enough, not because we have not tried hard enough, but because the laws of physics say no. The speed of light says no. Time dilation says no. Cosmic expansion says no. And those are not the kind of limits you overcome with better funding or smarter engineers. Those are bedrock. Those are the rules, and the rules do not bend. So what do we do with that? How do we live in a universe that is simultaneously infinite in scope and claustrophobically small in terms of what we can actually reach? One response is despair. If most of the universe is unreachable, if the destinations we care about are slipping away, if the cost of traveling anywhere interesting is losing everyone we know, then why bother? Why build the ships? Why plan the missions? Why expend the resources and the effort and the lifetimes of brilliant people trying to solve a problem that might not have a solution? Why not just stay home, accept our limitations, and focus on the problems we can solve? That is a rational response. It is also a fundamentally human response, because humans do not like being told there are places they cannot go. We do not like limits. We do not like walls. And when we encounter a wall, our first instinct is to find a way over it, under it, around it, or through it. That instinct has carried us farther than any other species on this planet. It has taken us from caves to cities, from wooden boats to spacecraft, from wondering what fire was to splitting the atom. The instinct to push boundaries is not a bug, it is a feature, it is what we do. And the fact that the universe has placed boundaries we cannot cross does not change the instinct, it just makes the challenge harder. Another response is acceptance. The universe is what it is, the laws of physics are what they are. We are not going to rewrite relativity, we are not going to stop the expansion, we are not going to build a ship that travels faster than light, because faster than light is not a thing. So we accept the limits, we work within them, we focus on what is achievable rather than what is not. We explore the local group, we map the Milky Way, we visit the nearest stars, we build colonies on planets within a few dozen light years of Earth, we spread slowly, carefully, within the bubble of space that is actually accessible to us. We do not waste time mourning the galaxies we cannot reach. We focus on the galaxies we can, and maybe that is enough. Maybe a few dozen galaxies, each one a treasure trove of worlds and phenomena and mysteries, is more than enough to keep us busy for as long as we exist as a species. Maybe the reachable universe is smaller than the total universe, but it is still incomprehensibly large by human standards. Maybe we do not need to visit every corner of the cosmos. Maybe we just need to visit the corners we can actually get to. That is pragmatic. It is sensible. It is probably the smart play, but it also feels like settling, like giving up on something important before we even really tried. The third response is defiance. The universe says we cannot go faster than light. Fine. We will go as close to light speed as physics allows. We will push the engineering to its absolute limit. We will build the ships, solve the problems, and launch the missions even if the cost is high and the timeline is measured in decades or centuries. The universe says time dilation is mandatory. Fine. We accept the cost. We say goodbye to the people we love, knowing we will never see them again. We step onto the ship, we make the journey, and we deal with the consequences when we arrive. The universe says the cosmological horizon is contracting. Fine. We prioritize, we triage, we visit the distant targets first, the ones that are about to slip away, and we save the nearby targets for later. We treat the reachable universe like a closing window, and we move fast enough to walk through it before it shuts. That is not a guarantee of success. It is not a solution to every problem. But it is a refusal to accept defeat without a fight. It is a recognition that the limits are real, but the limits are not an excuse to stop trying. And that response, that defiance, is also deeply human. We are a species that climbs mountains because they are there. We are a species that sails across oceans not knowing what is on the other side. We are a species that looks at the moon and decides we are going to walk on it. Not because it is easy, not because it makes economic sense, but because it is hard, because it is there. Because the act of reaching for something difficult and distant, and maybe impossible, is what gives the effort meaning. And maybe that is the answer. Maybe the point of exploring the universe is not to visit every galaxy or catalogue every star or prove that we can overcome every obstacle. Maybe the point is the reaching itself, the attempt, the recognition that we live in a cosmos that is vast and strange and mostly unreachable, and yet we try anyway. We build the ships even though the ships might not work. We launch the missions even though the destinations might slip away. We take the risks even though the costs are staggering. Because the alternative is to sit still, to look up at the sky, see all those distant lights and shrug, to accept that the universe is bigger than us and leave it at that. And that is not what we do. That is not who we are. We are the species that looks at the impossible and asks what if. What if we tried? What if we succeeded? What if the thing everyone said could not be done turned out to be doable after all? That question, that what if, is the engine that drives exploration, and it does not stop being important just because the obstacles are large. There is something else too, something harder to quantify, but no less real. The act of exploring the universe, of pushing against the limits, of trying to reach the unreachable, changes us. It changes how we see ourselves. It changes what we think we are capable of. When Kennedy announced that the United States would put a man on the moon by the end of the 1960s, the technology to do it did not exist. The rockets were not built. The spacecraft were not designed. The techniques for orbital rendezvous and lunar landing were untested. The whole program was a gamble, a very expensive, very public gamble that could have failed in a dozen different ways, and yet it worked. Not because the engineers were superhuman, not because the problems were easy, but because the goal was clear and the commitment was real, and the people working on it decided that failure was not an option. They solved the problems, they built the hardware, they tested and retested and iterated until the systems worked. And on July 20th, 1969, 2 humans walked on the surface of another world. That accomplishment did not just put footprints on the moon. It changed what humanity thought was possible. It raised the ceiling. It showed that the gap between here and there, no matter how wide, could be crossed if enough smart people worked together long enough. The moon landing was not the end of exploration. It was proof that exploration was feasible, that the limits were not as hard as they seemed, that we could do difficult things if we decided they mattered. Interstellar travel is harder than the moon landing by orders of magnitude. The distances are longer, the time scales are longer, the energy requirements are higher, the engineering challenges are more complex, but the principle is the same. The gap between here and there is wide, but it is not infinite. The obstacles are real, but they are not insurmountable. The laws of physics are strict, but they are not cruel. They do not forbid interstellar travel. They just make it hard. Really, extraordinarily, almost absurdly hard. But hard is not the same as impossible. And if history has taught us anything, it is that humans are very good at doing hard things when they decide those things matter. We split the atom, we mapped the genome, we built machines that think, we sent probes to the edge of the solar system and beyond. We detected gravitational waves from colliding black holes 1 billion light-years away. We imaged the event horizon of a supermassive black hole in a galaxy 55 million light-years distant. Every one of those accomplishments required solving problems that looked impossible at the time. Every one of them required decades of work, billions of dollars, and the combined efforts of thousands of people. And every one of them worked. Not on the first try, not without setbacks, but eventually, persistently. Because the people doing the work decided that the thing they were trying to do was worth doing. Interstellar travel is the next hard thing. It is the next mountain. And yes, it is bigger than the mountains we have climbed before. Yes, the summit is farther away. Yes, the path is steeper and the weather is worse, and the equipment we need does not exist yet. But the mountain is there, it is sitting in front of us, and we are the kind of species that looks at mountains and starts walking, not because we know we will reach the top, but because not trying is worse than failing, because the act of climbing, even if we do not make it all the way, teaches us things we would not learn otherwise, because the view from halfway up is better than the view from the bottom, and because maybe, just maybe, if we keep walking long enough, we find a path that works. We solve the problems, we build the ships, we make the journey. And when we arrive, when we step off that ship onto a world that no human has ever seen, we will look back at the distance we covered and realize that the impossible thing we did was possible after all. It was just hard, and even if we never build the ships, even if the technological wall turns out to be too high, even if the best we ever manage is sending probes instead of people, the effort still matters. Because the process of trying to solve the problem advances the technology. It pushes the boundaries. It creates tools and techniques and knowledge that spill over into other fields. The Apollo program was not just about landing on the moon. It was about developing the infrastructure, the expertise, the culture of solving hard problems under tight constraints. That infrastructure did not disappear when the moon landings ended. It fed into satellite technology, telecommunications, material science, computing, medicine, dozens of fields that had nothing to do with rockets, but benefited from the techniques and tools developed in the process of building them. Interstellar travel will do the same. Even if we never actually send humans to another star, the attempt to figure out how we might do it will generate breakthroughs in energy generation, propulsion, life support, radiation shielding, artificial intelligence, 100 other areas. The knowledge does not go to waste. The effort is not wasted. It compounds, it builds. And it makes us better at solving problems generally, not just the specific problem we were aiming at. But let us be honest, let us not sugarcoat this. The limits are real, the walls are high, and there is a very real possibility that we are stuck, Not forever, maybe, but for a very long time. Long enough that it might as well be forever from the perspective of anyone alive today. We might never build a ship that can reach another star within a human lifetime. We might never solve the energy problem or the fuel problem or the shielding problem. We might spend the next 1,000 years inching outward at sublight speeds, sending generation ships that take centuries to reach their destinations, colonizing the nearest handful of stars over timescales that dwarf recorded history. And that would still be an accomplishment, a slow, patient, multi-generational accomplishment. But it would not be the dream. The dream is faster. The dream is a ship that can cross the galaxy in a human lifetime. A ship that lets you see the stars and come back and tell people what you saw. A ship that makes the universe feel smaller, more accessible, more like a place you could actually visit instead of just look at through a telescope. That dream might not be achievable. The physics might say no in ways we have not fully understood yet. The engineering might hit a wall that no amount of cleverness can climb over. And if that happens, if we try for 100 years or 1,000 years and conclude that relativistic starships are not feasible, then we adjust. We accept the limits. We focus on what we can do. We colonize slowly. We explore carefully. We make peace with the fact that the universe is bigger than we will ever be able to traverse. That is not a failure. That is just reality. Sometimes reality says no. And when it does, you adapt. But here is the thing. We do not know yet. We do not know whether the walls are climbable. We have not tried hard enough to say for sure. We have ideas. We have proposals. We have simulations and models and back-of-the-envelope calculations. But we do not have data. We do not have test flights. We do not have prototypes. We are still in the phase where everything is theoretical. And in that phase, it is easy to be pessimistic. It is easy to look at the energy requirements and the engineering challenges and conclude that it cannot be done. But pessimism at this stage is premature. We do not have enough information to give up. We do not know what breakthroughs are waiting around the corner. We do not know what technologies will become available in the next 50 years or the next 100 years that will change the game. 50 years ago, nobody thought we would have handheld devices with more computing power than the entire Apollo program. Nobody thought we would map the human genome or detect gravitational waves or image black holes. Those things seemed impossible, or at least decades away. And yet they happened, because technology accelerates, because problems that look insurmountable at one moment become routine a generation later. That does not mean interstellar travel will follow the same path, but it means we should not assume it will not. And that brings us back to the question we started with: why travel? Why bother trying to reach the stars when the costs are so high and the obstacles are so steep and the destinations might slip out of reach before we ever build the ships to visit them? The answer, at least for some people, is that the question itself is backwards. The costs are high because the goal is hard. The obstacles are steep because the destination is far. But the difficulty is not a reason to avoid the goal. It is the reason the goal matters. Easy things do not change us. Easy things do not push us. Easy things do not require us to become better, smarter, more capable versions of ourselves. Hard things do. And interstellar travel is one of the hardest things we could attempt. It sits at the intersection of physics, engineering, biology, psychology, sociology, every field of human knowledge brought to bear on a single problem. Solving it, or even making progress towards solving it, requires us to function at the peak of our abilities. It requires cooperation on a scale we have rarely achieved. It requires long-term thinking, patience, persistence, and a willingness to invest resources into a project that might not pay off for generations. Those are not easy traits to cultivate. They are not natural. They require effort, but they are worth cultivating. Because a species that can coordinate on that level, that can think in those timescales, that can commit to goals that extend beyond individual lifetimes, is a species that can solve other problems too. Climate change, resource depletion, existential risks. The skills required for interstellar travel are the same skills required for long-term survival. And even if we never launch the ship, the process of preparing to launch it makes us better at surviving. There is also the knowledge. The universe is a laboratory. It is the only place we can study cosmology, test general relativity, observe the behavior of matter and energy under extreme conditions. Every galaxy we can reach is a data point. Every star system we can visit is a sample. And the more samples we collect, the better we understand the rules. The universe does not come with a manual. We have to figure out how it works by looking at it, poking it, measuring it. And the farther we can look, the more we can measure, the better our models become. Right now, our models are incomplete. We do not know what dark matter is. We do not know what dark energy is. We do not know why the universe has the structure it has, or why the constants of physics have the values they have. Those are not small gaps. Those are foundational questions. And the answers might be sitting out there in some distant galaxy, waiting for us to arrive and collect the data. If we never go, we never find out. We are stuck guessing, building theories on top of incomplete information. That is better than nothing, but it is not the same as knowing. And the only way to know is to go look, to visit the distant structures, to measure them up close, to test our theories against reality in places where the conditions are different from what we have here. That knowledge is not just intellectually satisfying, it is practical. Understanding how the universe works gives us leverage. It lets us manipulate things we could not manipulate before. It lets us build things we could not build before. It opens doors, and some of those doors might lead to solutions we have not imagined yet. Solutions to problems we do not even know we have. The history of science is full of examples where a discovery made for purely theoretical reasons turned out to have practical applications decades or centuries later. Relativity was not developed to fix GPS. Quantum mechanics was not developed to build computers, but both of those applications emerged from the theory, and both of them have transformed the world. The next breakthrough might be sitting out there in a galaxy 10 billion light-years away, and if it is, the only way we find it is by going there. And then there is the perspective, the overview effect. Astronauts who have flown to space and looked back at Earth from orbit describe a shift in how they see the world. The borders disappear, the conflicts look small, the planet looks fragile. That shift is not just poetic, it is psychological. It changes priorities, it changes what you think matters, and the effect scales. The farther you go, the more pronounced it becomes. Imagine looking back at the Milky Way from outside, from a vantage point in another galaxy, or from the far edge of our own. The galaxy would look like a spiral of light, 100 billion stars swirling in the dark. And somewhere in that spiral, so small you could not possibly see it, would be the sun. One star among 100 billion. And orbiting that star, invisible, insignificant, would be Earth. Everything you have ever known, everyone you have ever met, every war, every invention, every triumph and tragedy in the entire span of human history, all of it confined to a pale blue dot, so small it would not even register as a pixel. That perspective is humbling, it is terrifying, and it is necessary, because it reminds us that we are not the center of the universe, we are not even close, we are a footnote, a brief flicker of complexity in a vast, uncaring cosmos. And that realization, as uncomfortable as it is also clarifying. It tells us that the things we argue about, the things we kill each other over, are not as important as we think they are. It tells us that the only thing that really matters is whether we survive, whether we figure out how to keep going, whether we expand beyond this one fragile planet before something happens to it. And the only way to expand is to reach the stars. That is the end game. That is the long-term survival strategy. And the sooner we start, the better our chances. So we are left with a choice. We can look at the limits, the three walls, and conclude that the universe is too big and too hostile and too indifferent for us to ever really explore it. We can stay home, we can focus inward, we can accept that we are a one-planet species and make the best of it. That is an option. It is a valid option. And maybe it is even the right option. But it does not feel right. It feels like surrender. Like admitting that the universe won and we lost. And maybe that is fine. Maybe losing to the universe is not a failure. Maybe it is just an acknowledgement of scale. But it also feels like we would be leaving something on the table. Some possibility, some chance, some version of the future where we did try, and we did build the ships, and we did make it to the stars, and we found something out there that changed everything. That future might not be real, it might be a fantasy, but the only way to know for sure is to try. And if we do not try, we will spend the rest of our existence wondering what if. What if we had built the ships? What if we had taken the risk? What if the thing we thought was impossible turned out to be possible after all? That wondering is its own kind of cost. And it might be higher than the cost of trying. The universe is vast, it is ancient, it is indifferent. It does not care whether we explore it or not. It does not care whether we survive or go extinct. It will keep expanding, keep pulling itself apart, keep erasing the evidence of its own history, with or without us. We are not special to the universe. We do not matter on cosmic scales, but we matter to us, and that is enough. That is all we need. We are a species that looks up at the sky and wonders what is out there. We are a species that builds tools to answer that question. We are a species that takes risks, makes sacrifices, pushes boundaries, because the act of pushing is what makes us who we are. The universe might say no. The laws of physics might say no. The engineering might say no, but we do not know yet. We have not tried hard enough to know. And until we do, until we exhaust every possibility and solve every problem we can solve, and push the technology as far as it will go, the question remains open. Can we reach the stars? Can we cross the galaxy? Can we visit the distant places before they slip out of reach? Maybe, maybe not. But the trying is what counts. The reaching is what matters. And even if we never get there, even if the walls are too high and the limits are too strict, the fact that we tried, the fact that we looked at the abyss and decided to build a bridge across it anyway, that is the story worth telling. That is the legacy worth leaving. That is our place in the unreachable cosmos. Not conquerors, not masters, just travelers, dreamers. Explorers standing at the edge of the unknown, staring into the dark and asking what if. So here is what we know. The speed of light is the fastest anything can move through space. Time dilation is real, confirmed, measured down to the nanosecond by clocks flown on aeroplanes and particles spun through accelerators. At 99.9999% of light speed, you could cross the Milky Way in 50 years of your own time, while 100,000 years pass outside. The physics allows it. The engineering does not yet, maybe not ever. And even if we solve the fuel problem, the shielding problem, the navigation problem, even if we build the ship and launch it and survive the journey, we arrive in a future where no one is waiting. We step off into a world that has moved on without us. That is the bargain. That is what relativity offers. Not faster than light travel, Not a shortcut, just a way to skip forward through time while everyone else lives through it at normal speed. And behind all of that sits a larger problem. The universe is expanding. Dark energy is pulling it apart. The reachable universe is shrinking. Destinations that are accessible today will not be accessible a billion years from now. The cosmological horizon is contracting, and every galaxy that crosses it is lost. Not destroyed, just gone, forever out of reach. No future technology will bring it back. So we are not just racing against our own limitations. We are racing against the geometry of space-time itself, against a universe that is slowly, patiently, inexorably erasing most of itself from the set of places we can ever visit. The window is closing, not quickly, not catastrophically, but inevitably. And the question is not whether we can reach every corner of the cosmos. The question is whether we will reach any of them, whether we will look at the limits, acknowledge how steep they are, and try anyway. Because the trying is the point, the reaching is the point, and maybe we fail, maybe the walls are too high, maybe we are stuck here, bound to this one small patch of space, watching the rest of the universe recede into the unreachable dark. But maybe we are not. Maybe the thing that looked impossible turns out to be hard instead of forbidden. And the only way to know is to start walking, to take the first step, to build the